Okay. You want to track Canadian IYPT live stream?
Okay.
How is it?
Streaming. Can we start? Okay. This.
I guess you can start, but the rest would like to know the address. Yeah, you can go to YouTube and search for CYPT.
It's, you know, like, the thing is, like, the guys who are sitting here don't really need the rest of the stream, no? It's more for the. Like, we will send out, like, we're running a few minutes. We still have, you know, the introduction preparation. Like, I don't think this is. I think, like, generally they know what to do. It will last a few minutes. I think in that time we can start. Otherwise, we'll have to skip lunch or something. You know, like dinner. They're used on it already, you know? Okay, so welcome everyone. Welcome to the finals of the 35th Young Physicist Tournament 2022. I guess all of you know me already. Young Physicist Tournament, and I'll be the guy who's responsible for this morning as the chair of the jury and who makes the final here. For those who know, IYPT is a competition for. This is a team competition where we do solve open problems, and here at the very top of the pyramid, 3 best solutions of the teams worldwide. Teams participate into account all the problems we had this year with running COVID and with running war. Okay, and yeah, I'm really glad that. And also thanks to the other teams who came here to watch the finals. It's great because I think you'll see what you have to do next year to be here or in a similar scene, and it's also a nice show of respect to the teams which are sitting here. So I don't want to speak longer anymore, and as we still have just one microphone, I hope to get more, say before the discussion. I just turn to this mic and pass this running microphone to the captain of the Swiss team, who will be starting with the report this morning.
Hello, I'm the captain of the Swiss team. My name is Jan Kamps, and my team members are Joel Van, Anja Duvel, Jason, and last but not least, we wish you the best of luck with the teams. Thank you.
Sorry, I don't think this. And can we get rid of this feedback noise? Okay. Anyway, Veronica. Opposing team Poland. I'm sure you would handle that. You'll get it right. Welcome, ladies and gentlemen. My name is Janowicz, Poland. In our team, there is Igor Kumela, Maciej Zambrowski, Mikołaj Czapecki, and Rafał Berg. everybody good luck, good physics fight, and for thank you. Thank you very much. And last but not least, we have the reviewing team from Singapore.
Hi, James from Team Singapore, and here are my teammates Martin, Jet, Zindo, and Sigrid.
Thank you very much. For those who are not that much familiar with our rules, these three teams always competed in the selection final, so these are the three teams who ended on the three best place, and they are appearing here in the reverse order, so normally one could say the second place and the reviewing team on the first place after the selection fights. This is not completely true. I'm at IYPT for more than 20 years, but it never happened before that the regulations would not allow to select between two teams in some place decision. We had both Polish and Swiss team with the same number of points and with the same number of five. So we made a draw of lots yesterday in the evening to define the order of viewing in this round, but it's not a big issue. Finals we start from zero level, so whatever happened in the five physics fights is forgotten, almost forgotten, and they survived in the order of appearance here, and the teams start from the same level. The winner of the finals will be the team who gains most of the points from the jury sitting here, and that's the jury members, please.
Good morning, my name is Fan Yulo from Taiwan. So I'm involved in the fight this morning. Thank you very much.
Good morning, spectators. My name is Michael Steck. I have been the head organizer of the German national competition and the team leader of Team Germany for almost 10 years, and I wish you the best of luck as well.
Good morning, my name is Erin Harper in Wellington, New Zealand. It's a real privilege to be here and meeting you amazingly talented people. I'm looking forward to seeing what you and I'm a little bit terrified.
Hi everyone, my name is Jim. I'm from Canada. I'm a past participant, and currently I am a cadet scatter visit graduate student. Everyone have a wonderful life.
I'm also from New Zealand as a high school teacher. Worked with training the New Zealand team for many years. And also to guys in the area, so I'm forward to see that's what she's forward to.
My name is Peter. I am from Hungary. I'm a physicist in the social lab, and I wish you good luck.
Hi, I'm a physics teacher at the German School of Budapest at University. I've been involved in IYPT since 2000. Wish you all the best.
Hello everyone, I'm Natalia Ryszkova, I'm from Slovakia. I'm a participant since 2014, I believe. I'm a PhD student and study physics, and I wish everyone a great final fight.
Okay, thank you very much. So I introduced already myself, and I'm also a former participant from the last millennium. And since that, team leader, country coordinator, secretary general, currently the president, I work mostly as a physicist in Slovakia and two other places. And it will be my pleasure to test the physics edition of today. So we are anyway a little bit behind schedule. To make the preparation of your report. 5 minutes for preparation. It will start at clock. Here on the right hand side, you'll always see the clock with the running phase. Time's over for preparation, we immediately start the next stage. If you're not ready, your time is running. If the time for a stage which is active is over, then I'll finish a reasonable sentence, so to say, not that much more. And especially if you are asking the question, it might be wise to reconsider starting asking the question a few seconds before the end, otherwise it usually stays unanswered. Okay, stage is yours, 5 minute preparation.
Should we announce the link? Does everyone know the link?
I'm sharing it on my Insta. I don't know where else you want to put it.
Can I check everyone? Do we all know the live stream link? I know you are watching, but maybe your friends. Do we all know the link? It's on the Canadian IYPT YouTube channel. Canadian. You'll see a thumbnail of me like doing that's the one.
Okay, everyone heard. So the message was that it's only Canadian young businesses that I'm inside that will on the YouTube channel, sorry, and we try probably to post the link there in our Instagram as well, and also put it on our website, so at least we get something.
Just filter for the it doesn't do it.
Oh, I see.
Just comment. I think I can turn on.
I'm curious. Is there a camera interface straight with the laptop? Interface straight with the laptop?
I don't know. There might be something like AV. I think I said HDMI.
Okay.
There could be.
Okay, search it up. If it does, you want to just stream it to the laptop? Or do you want to?
I'm actually recording.
Okay,
so
you want to?
I don't know if recording and live stream can go at the same time. Maybe.
No, I don't think so. But yeah, it's up to you. Yeah,
All of the video ones will stay up on the channel.
yeah, this live stream stays up.
I wonder if I should hide all the chat.
Oh, for us.
Yeah.
Yeah.
So you can see better. No, this is a high school teacher.
Oh, okay.
In RI, Raffles.
Oh, Raffles.
It's a very cool car.
Anytime you're ready, you're welcome.
I think hopefully.
Morning everyone, I'll be reporting on Droplet explosion fault number 10. Let's go to the task statement. When a drop of a water mixture, for example water alcohol, is deposited on the surface of a hydrophobic liquid, for example vegetable oil, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. So phenomenon are that binary droplets with self-atomize an oil carrier. So we tested various liquid substrates and found that using sunflower oil as our substrate and a binary droplet composed of isopropyl alcohol and water is most optimal because we can easily recreate the phenomenon, and this is what we base our investigation on. The task is to investigate the dynamics of the behavior of the mother droplet and also the daughter droplets. So let's define this. The mother droplet is the central big large droplet which has a radius r. The small daughter droplets are ejected at the periphery of this mother droplet, and we also define a phenomenon timescale which is the necessary time for the mother droplet to fully self-atomize. Our goals are to formulate proportionalities describing the mother droplet using dimensional analysis, and also to investigate the behavior of daughter droplets under priority variation. Let's go over to our theory. The first part will consist of the numerical. Let's give a qualitative explanation of the phenomenon. When we initially place our droplet on the oil bed, we can use Young's equation to relate the solid liquid, the liquid gas, and the solid gas interfacial surface tension. When Young's equation holds true, a droplet can be constituted. But for our case, this cannot hold true. What happens is that gravity dominates the surface tension. Therefore, we get this bubble-like structure where we say that the contact angle has to be conserved, as this is energetically preferred and therefore shearing occurs. What also occurs is that at the periphery, the ratio of the surface area to volume compared to the center is much bigger, and therefore there's a preferential tendency for evaporation to occur there. What this leads to is a surface tension gradient, which drives the Marangoni flow. This can also be associated with the initial concentration or mass fraction of the alcohol. So when we place our droplet on the oil, the finger-like structures start to appear. Now, what we can say is that our periphery has the critical concentration by C, and liquid then flows from the center to the periphery and penetrates this periphery. Energetics prefer a smaller droplet to form. Energetically favored at some point for water droplets to be ejected. Now, for the final stage of our qualitative explanation, you see that our droplet recedes at some point in time, which we can dominate the RPA. So a droplet fully self-atomizes. Also, we say that the small, when they are ejected, still shrink over time. We are saying that they have the mass fraction is higher than the critical value, so the shrinking with evaporation still occurs. Let's go to the governing proportionalities given by literature for the characteristic radius and the timescale, where we relate the characteristics correctly to the initial IPA mass fraction, the critical IPA mass fraction, the initial droplet volume, and the surface tension gradient, which are all droplet properties, and also the oil bath depth and the dynamic viscosity of the mass velocity. We now have to discuss what assumptions we make to get these proportionalities and how to derive this. First, we look at the friction in the system. This, we can assume the viscosity, and consequently we can relate the Marangoni shearing force in the oil. Therefore, we have a driving pressure. We can write an expression relating to the driving pressure of the Marangoni flow and the counteracting shear pressure of the oil. We also know that there is an expression for the shearing oil pressure or force, which is called the Couette flow. So consequently, we have two expressions for the shear force, which we can then solve for the spread velocity, and we also know about velocities that they are displaced over time, which in this case would be our radius over our time scale. These are the first two proportionalities we need for formulating the governing proportionalities. Next, we look at the evaporation, where we say that the water mass in our system is conserved. On the left-hand side, we have the water volume at T equals 0, and on the right-hand side, we have the water volume when the phenomenon has completed. This is our third expression. Finally, we can write the evaporated IPA mass as this. In literature, we get another equation for the evaporated IPA mass, which we can solve for the mass transfer velocity. We can then write in a proportionality relating the evaporated IPA mass with the mass transfer velocity, the section area, and the time scale. This is our final proportionality, which we need, and with these four, when we combine them, we get the following two expressions that I've shown before. And now we want to very experimentally if these governing properties actually describe a phenomenon. To do this, we use a precision pipette to place a binary droplet onto an oil pool, which was in the petri dish. And under the petri dish, we had an LED light pad, which was placed there for better contrast when imaging. We started with a hypothesis for the experimental investigation, where we say that the maximal radius must be proportional to the characteristic radius. The maximal radius, to remind you, is the maximal value the radius of the mother droplet attains during the phenomenon. And also we say that the characteristic time scale is proportional to the maximum time scale, which is the necessary time for the phenomenon to fully complete. Now, we see that our governing proportionalities actually do predict the same behavior for the maximal radius, where we say that in the initial mass fraction, in this case here, has a positive relation for the maximal radius, but there needs to be a minimal value, which is our phi c. Similarly, for the old depth, you can see that there's a positive relation for our max over T max, as a negative correlation. This has to do with the decreasing effects of the lowest glass layer of our petri, which has a big impact on the friction. With these two variations, we can predict our critical phi c, which we predict by plotting Rmax versus the initial mass fraction and vary the oil depth and the initial mass fraction systematically. And we can see that at the x-axis intersect, we get the values or the predicted values for our critical mass fraction, where empirically we found that it was around 0.35. This is also supported in literature, and we have now a corresponding error as well, so our prediction is a novelty. Next, we want to find for our maximal time and our maximal radius, where we can plot the maximal radius versus the characteristic radius, and find that the proportionality constant is 1. So we can measure the left side and then predict what our maximal radius would be on the left-hand side. So we can have the same predict for the maximal time and then predict what's on the left-hand side. Categorize our mother topic, we would now like to move on to the dot topics. So the sophomore ability is the formation an interface between a viscous and a comparatively less viscous fluid. The capillary length is an expression to describe the distance between two of these differences which occur at the rim of the initial mass fraction capillary length. We see that there is a vertical asymptote at the critical IPA mass fraction. This means that the capillary length is a second reference for the objects, so we can quantify our Doppler droplets. Speaking of Doppler droplets, we would now like to see a certain parameter. When we increase the initial IPA mass, the number of droplets increases and also their size decreases. The size decreases because the overall surface tension is lower. There's more alcohol, so the alcohol component is bigger, and therefore the overall surface tension of the mixture is lower. Therefore the constituted size of the droplets, the maximum size, is smaller. But the volume over all these measurements are constant, therefore we have much more droplets. For the variation of the oil depth, we have increasing from left to right. We see a similar trend where we can explain the smaller droplets by the necessary momentum they have to bring to overcome the friction. So at higher oil depths, we have less friction because there are more oil layers that can be sheared. The effects of the glass lower on the drawing is significantly less. Finally, for the variation of the initial droplet volume, we can state that when we have more volume, we have basically a bigger reservoir. The reservoir leads to a bigger maximal radius and a constant capillary length, which is an assumption which is justified. Seeing that the initial IPA mass fraction is the same, we have more jets. More jets leads to more fingers leads to more droplets. Finally, we can also look at the Doppler droplet size distribution, where we use a cell tracking program, where we basically make our picture binary, and then we see we can get the size distribution of our Doppler droplets, where we see that the smallest Doppler droplets are the most numerous, they have the most time to evaporate. And also we get this staircase-like structure which is seen for every self-atomized product. So in conclusion, we have expressions for the characteristic radius, which are given from literature, but we give the derivation also the assumptions of these first characteristic phenomena for characteristic proportionalities. Then we predicted our critical mass fraction, which we found also to correspond to the empirically found value. We next plotted the characteristic dimensions versus our maximal dimensions, and gained proportionalities, which not proportionalities, equations actually, where the right-hand side, we can measure all of these properties and predict what our maximum radius or our maximum time will be. Then we look at the capillary length, which is a multiplication of our fingers and also consequently the smaller water droplets, where we have a vertical asymptote and it is a second reference for the critical IPMS fraction. And finally, we look at the total droplet size distribution using a cell counting imaging program, and we also investigated the behavior of the dollar droplets when comparing the initial concentration, the volume, and the order. Here are my references. Thank you very much for your attention.
Thank you. Thank you very much. Now we have time for the questions from the opponent. Please, team from Poland.
Hi, so first question, what was the maximal concentration for which this phenomenon occurred?
So we found it to be around 85%. So if we look at the concentration which has 106,
85%. And was it mass concentration or volumetric concentration?
Mass concentration.
Okay, mass concentration. And what was the evaporation rate in your experiment? So parameter JV, I guess.
So if we go to slide 17, what we basically did is we took a...
and how did you determine? We determined it by measuring mass dependence in time, right?
Yes, so if we go to 69, we have another setup where we vary the width of the second, and then we can control how much...
I agree that this is the proper method. Have you tried to obtain this phenomenon without evaporation?
No, because that is the most crucial.
Okay.
One of the most crucial parts.
This is the most crucial part of the phenomenon. All right.
Yes.
And you observed outer portion of droplets, and it was because of viscous. Because there, yes, so we observed it. So,
sorry,
what was approximately the Marangonic flow velocity?
The flow velocity?
Yes,
the order of magnitude would be around 10 meters per second.
10 meters per second. Marangonic flow velocity noted. Okay. And did you used how many alcohols did you use?
I used so if you go to slide 3, we use isopropyl alcohol and also ethanol. So if you go to the
two alcohols.
Yes.
And so once more, which instability causes the formation of fingers?
Sorry?
Which instability causes the formation of
Submaterial
fingers?
instability.
Okay, submaterial instability. And what did you use to color your mixture?
We used methylene blue, so if you go to slide 76.
Okay,
that's chemical formula.
Okay.
It has the same density as water.
Okay, thank you very much. Thumbs up for the questions, and now we have 3 minutes for preparation.
I thought you wanted to listen to it. As it might just be into the picture.
Well, I might have
So it's a USB-C converter.
Yeah.
And I'm charging it. Okay. It's alright, it's alright.
They're complaining as They're complaining as
Too soft.
Yeah, hey, let me have it here. First, let me figure out how the zoom actually works. I feel like there should be some actual way to zoom. Okay. So once you put your fingers on it, it just jumps. And then you just smoothly.
Super sensitive.
Could I kindly ask the audience to call down, because the teams need to prepare. They have a hard work, and if you are very noisy, it's hard for them. And can I ask for technicians to help? Veronica, there's a power plug needed in the front. Yes, this is something we should have. checked before, but still have 1 minute to fix the problem.
It's good.
Is it?
Hello. Okay, so ladies and gentlemen, I'd like
Okay,
to
please, I ask you to start. Okay.
I'd like to present to you our opposition to problem number 10, droplet explosion. So the problem content states that we have to investigate drop that sometimes fragments into smaller droplets. So the main focus of this problem should be smaller droplets that form in this phenomenon. So we had a drop of water mixture that is deposited on the surface of hydrophobic liquid, and then it may sometimes drop into smaller droplets, and we have to investigate what parameters affect the fragmentation and size of droplet. I think that the investigation of conditions for this phenomenon to occur was done partially, because, for example, we don't believe that the maximum concentration was done well. Also, we think that fragmentation to smaller droplets wasn't done really well. We don't believe the condition for the explanation of fingers, and we think that this should be talked about more in discussion. But we think that parameters affecting size of droplets was done very well. We can see when different scaling laws introduced and many different parameters changed. So in this problem, what we like was quick analysis of different liquids and state which liquids were working the best. We also like that they introduced surface tension and working phenomenon, and we believe that they are the most important part of this problem as the cosmogonic law, and we like how it was stated why the difference between effects due to evaporation. We like how they introduced motion of oils to talk about how smaller droplets fragment and they have their own velocity after detaching from fingers. We agree that the smaller droplets occur because of breakaway instability, so they have less potential energy than the fingers, since they have small. Yes. Well, and also we like how they measure the evaporation rate, hoping that this is the best way to do so. They also change initial concentration of alcohol and initial volume and thickness of oil, which we like. What we didn't like is only an investigation of creation of fingers. So in papers about submaterial instability, it is said that it occurs when you increase or decrease amount of liquid, and we think that maybe they should try to do this increasing or decreasing artificially, not through evaporation, to be able to rule this out and to check if you can do this another way. We think that too little time was spent on little droplets. Half the presentation was spent on mother droplet, and we stated before that this isn't the main focus of this presentation, of this phenomenon. It shouldn't be the main focus of this presentation. The philosophy of parametric flow, we didn't see any measurements, but we saw some that you would like to talk about, and you would like to inquire about methodology of that. Also, the conclusion to experiment was limited, and there was only one measurement for the size of final droplets, which should be the main focus of the presentation. They also did analyze how often those droplets detach from fingers. So we'd like to see maybe analysis of concentration of droplets more, or frequency with which they detach from fingers. It could be an interesting parameter. And there was also no explanation of why droplets might not be circular. In some videos we saw that it isn't circular and that the droplet distribution is not symmetric. There are higher droplets away from thanks. I'm glad to report this.
Thank you very much. So now we start with the discussion. Please, 10 minutes.
Okay, so
Please use your microphones.
okay, so could we please quickly talk about what Safran-Taylor instability is?
So the Safran-Taylor instability for our case is the formation of fingers. I think you did not understand what I mean when I say the Safran instability is for the fingers, because the condition for this to occur is to have a viscous liquid and comparatively less viscous liquid.
Yes, so what is the difference in viscosity of liquids? When you have liquid to quantities, so when this viscous liquid is injected from 1 versus 1, it occurs, right?
That is correct. But the fermentation to the planetary instability.
Okay, so which liquid has the highest viscosity in your system?
Plus oil.
It was oil.
Plus oil.
Okay, and so we decide let's use oil from more which is oil, right?
Sorry?
We saw, but the Safran-Taylor instability occurs when which liquid is decreasing or increasing this.
No, it's not increasing or decreasing. There's two different liquids, and one has a higher viscosity than the other. It's not that it's changing. It's not dynamic in that
Okay,
sense.
so you state that Safran-Taylor instability occurs when we have just one liquid and other liquid, and they have different viscosity.
That is true.
And
But the viscosity difference must be quite significant.
Okay. We believe that for Safran-Taylor instability to occur, you have to be either sucking liquid or injecting liquid.
No, but the thing is that our fluid from the middle is ejected through the periphery because of a concentration difference from the rim to the center and also a surface tension gradient.
Okay.
So this is very
We try
important.
to limit evaporation, maybe introducing some sort of baths of concentrated air in which your fluid will evaporate, and then try to simulate your evaporation manually. So, for example, through sucking via syringe. We believe that this would be able to.
I did not use this specific setup, but I did investigate evaporation. So if you go to slide 69, our setup was like this. Basically, we have a dish on an S on a scale, and then we have a fan above it.
Yes,
we measure the velocity of the airspeed. We measure the velocity of the airspeed, and then we track the evaporative mass from the slide. So if you go to the next slide, that's 17. You can see that the values with equal
Okay. Yes, I see that. So I see that you investigate how your fluid decreases through evaporation. But I think that Safran-Taylor instability works when you increase the amount of less viscous fluid or which is one. But maybe just want to different aspect of your presentation.
Okay, sure.
Please see quickly slide number 33, where there are.
Yes.
You can see here that you can see pictures of your final droplets.
Correct.
And maybe slide 34, please. Could you identify the biggest droplet in this slide?
So I think it was around 8 millimeters for this specific.
Oh, yes, I think that it was.
But this is case.
So you say through your experts, through your graph that the biggest droplets occur in the center of your mother, in front of your droplet, right?
I mean, that is plenty, but that's not what the graph says. The graph is just a percentile distribution of the sizes.
And what are your predictions for size distribution then?
My predictions are that the smallest droplets are the most numerous, and also we have this staircase-like structure, which we can explain with the following. The time necessary for the minimal size to occur is significantly less than the entire time scale, and therefore this type of smaller droplets can accumulate, and therefore it's the most numerous.
Okay. But how would you explain? Because I think also what was the size depends on diameter, on distance from the center of the droplet.
So because if we have a center, the ejected ones were ejected first, and therefore there's a longer time to evaporate, because therefore they are smaller, significantly smaller than the last droplets that are formed.
So you state that it increases with distance from the center?
Yes.
Okay.
Just keep the mic close.
Okay.
When you take a picture and when the time scale is complete, so when the phenomenon or when the multidrop fully self-optimizes. Of course, when you look at a given point during a given time in the phenomenon, the size distribution might be slightly different. But this is at full self-optimization.
Okay, don't you agree that I think that on this slide, and slide 33,
So then,
which one we see that? This slide. I think it can be clearly seen that your size of droplets is asymmetric. So, for example, on the leftmost picture, I think the bigger droplets appear on the left side of
no, but I think you're confusing something. So I did not mention this in the presentation, but our white bar is a scale with the same length. So if you see the rightmost picture has a significantly less smaller bar, they all define 1 centimeter. So if you compare them, they are roughly the same size.
Oh, so do you have any explanation for why this distribution might be uneven?
Because it is a quasi-equilibrium, so this is like an instability, right? So it's not perfectly uniform, but that is why we also use averages for I guess, the distribution. Yes, preferentially in the center, because they are the last droplets to form. And at the least time to evaporate to the minimum size.
Okay. I think that this would be different of course, since I don't think that what was the method we should use for investigating the size of droplets.
So we use the cell counting program, so it's 34. And what it basically did is gives us, so we made a picture binary, so black and white, and then the program will then count the pixels of each droplet, and then we can relate one pixel to one length dimension, and then get the size distribution of our droplets. So it gives us a percentile distribution of the different sizes.
Okay, can we go to slide number 25?
25.
What was the value of scaling constant in this slide, in your method on the left?
I do not have the specific constant, but this is also not really important because we can get our final constant if we go to slide 28, and we can see that it is 1. So it might be good to look at each of the constants individually, but for a formula for the maximum radius, which I think is a really strong part of our report, it can. So if we measure everything on the right-hand side, we can predict the maximum radius. And this suffices, in my opinion.
Do you think that your measurements agree with your linear field?
I mean, the oil depth variation is slightly off, so the orange.
Yes, it seems like oil has higher inclination and...
slightly.
Yes.
But I think generally the trend is...
well, it's literally outside of your error bars. What do you think could be source of this?
So if we go to slide 26, you can see that these points here don't fully match.
Yes, and why do they don't align?
They do not align because we say that the effects of lower oil depths at a certain limit become negligible or almost negligible. Therefore, there must be a limit at which our theory can predict with the oil depth how it will behave. However, I think, I guess this is one limitation for the oil depth specifically, but I think for the other parameter variation, this is fully acceptable.
So you say that there is some maximum molecular depth for which your prediction is not accurate.
Correct. This has to do with the magnitude of the driving force. So how many layers this driving force can actually shear. The oil depth at which the layer actually still experiences this force and gets sheared.
Okay, I agree. But do you have limitations in other ways? So it's maybe the minimal thickness of oil for which you might have.
So, of course, if we just take the glass Petri dish, we go slide 3, we can see that, oh sorry, we can see in the figure F, which is here, that this is no longer our phenomenon. We no longer see an ejection of water droplets, which I would say is our limitation.
I think that it will be investigated. It will be nice, for example, to see how it would happen on kind of surface tension. I think that makes sense to how you investigated surface tension. Because it's one of the most important parameters.
I see. So we do not measure our surface tensions.
So how would you
investigation?
Well, it changes ratio of your alcohol in your water concentration.
That is correct. So we can just take values from literature, I guess, and then.
Okay, thank you. Thank you. That was the last question and the last answer for this discussion. And the opponent has now 1 minute to summarize the discussion. Please.
Okay, so I think that the biggest flaw of this presentation is that the phenomenon of creation of fingers was not explained well enough. I think that submarginal instability is more complex than further stated, and the difference in viscosity is very important, and increasing injecting or sucking of liquid, and he should make experiments where he doesn't have compression in his setup at all, and he changes this by different in different way. We think that he should measure surface tension for his liquids, because I think that Paris formulary pressure might not always agree, because for example you add also in to your liquid, and it will change now.
Okay. Thank you very much. Time for questions for the team of reviewer, please.
Right, so to the reporter, can you please 30. 30, sorry. Yes.
This instability is caused by a difference in viscosity. But in this term here, where is the viscosity? Is the rho the viscosity?
It's the density.
But you said that this is the
first is a difference in viscosity.
To the opponent, do you think that if the phenomenon shouldn't be an
Can we change the mic?
So to the opponent, if the phenomenon is caused by viscosity, do you think that viscosity should be in this equation here?
So should it be included in this equation?
Yes.
In submarginal, yes, it should be, because it is important to this phenomenon.
Alright, so to the next point. To the reporter, I think you mentioned that gravity is the cause of the initial spreading.
No, the lack of surface tension to counteract the gravity is the cause of the spreading.
So what we're saying is that because the surface tension can hold the droplet, it was therefore to this.
Correct. It spreads into a quasi-puddle. It cannot constitute the form of a droplet.
To the opponent, do you think that there are other factors that could cause the spreading? That forces?
So for example, it could be differences in evaporation rate, and the fact that the liquid would evaporate slower from fingers than from droplet.
Sorry, may I clarify? The initial spreading of the droplet is due to the lack of surface tension, but then the occurrence of the phenomenon is due to a difference in the evaporation rate from the center to the periphery, which causes the surface tension gradient and the concentration gradient.
To the opponent, do you think it's possible that the adhesive forces between the oil surface and the water droplet will cause the spreading?
So differences in oil surface and
the adhesive forces between the oil surface and the water droplet, do you think that it will also cause the spreading?
I think this isn't the main force that drives this phenomenon.
I see. Alright, so to the reporter, you mentioned that your flow velocity was 10 meters per second.
Yes, I would like to correct that. It is 10 to the minus 2 seconds. I misspoke.
Wait, so 10 to the minus 2 meters per second?
Meter per second, of course, because it's a velocity.
So 0.01 meters per second. Alright, understood. So could you...
sorry, that's an order of magnitude. That's not a specific...
order
of actual order.
Sorry. Alright, so you use a probability for all of your equations and your predictions. So does this seem...
Sorry,
so like you had a proportionality
proportionality, yes.
Yeah. So does this, for example, you have a constant term, like this coefficient term in front of your proportionality term, yes?
Correct.
So does this constant term, like, is it the same for every single different parameter, or like every single different experiment you conducted?
Yes, because if we go to slide 44, if you look at each measurement, it collapses onto a mass curve, so this shows the scalability of the phenomenon, and it does hold true.
Okay, thank you very much. Time for questions out. Now we have time for preparation.
Yeah.
can I kindly ask the audience to calm down and let the teams and jurors work in a calm environment? Thank you very much. Okay, please start your review.
Right, so good morning everyone, I'm IYPT, and today I'll be reviewing problem number 10, droplet explosion. So on to the report. The reporter correctly attributed the breakout of mechanism to instability and stated that the figures formed due to instability. And he also had good experimental control, which correctly determined the evaporation rate using the mass of the droplets. And he also used a method to accurately vary the drop volume. And thought it was very commendable. These are important parameters to be very experiments. And he also had a lot more data analysis, where he used edge detection to do droplet tracking, and this allowed him to measure droplet size accurately. And he used a very wide range of parameters, such as the alcohol penetration, droplet volume, and oil thickness. However, there is area for improvements. Firstly, he gave an unsatisfactory qualitative explanation, where he said a very dominant substantial in the sheet and called spreading. However, I believe that it is instead an adhesive forces between the oil surface and the water droplet that causes the initial spreading instead of the gravity. And he also very strong qualitative explanation for the formation of figure-like structures. We only attributed that to a substantial instability and did not explain further. And he also did not explain what water droplet recedes inwards, and this is called by volume loss of the drop. And he had most simplifying assumptions such as this spreading velocity and a highly empirical model, which provides less physical insight phenomenon. And he had no theoretical prediction for the droplet distribution, which can be easily theory as the spreading radius of the drop and the figure and the weighted order figures and their instability, which could be used to model this phenomenon. And he also did not explain the critical quantification qualitatively. So on to the opponents. The opponents pointed out unsatisfactory qualitative explanation of the figure formation and pointed out the spinning constant use, which I thought decreased the predictive power of the report. And he already pointed out the unsatisfactory investigation into the final droplet distribution. However, he has some points, such as he did not really states the highly empirical model and unsatisfactory qualitative explanation, where he did not notice that the point of clarity where it does not dominate this tension, and he did not also qualitatively ask for the droplet receiving inwards. So now on to the discussion and analysis. The first one was on the simultaneous instability, where the opponent said that it was not applicable because the liquid needs to be sucked or ejected. In this case, I partially agree with the reporter, because the liquid is indeed ejected, and therefore I believe it's similar to what the opponent has structured the condition which allows the instability to be applicable. And all the structures that average will cause the phenomenon to occur if the qualitative is correct. However, in the expression for the wavelength instability, there was no viscosity terms, and I thought that this was very suspicious, as they said that instability is caused by viscosity, but there was nothing potential about viscosity inside the distribution. So on to the next point. The opponent raised the point that the final droplet distribution is not uniform, and the opponent mentioned that the droplet split is further from the center and smaller due to longer evaporation time. And I partially agree with the reporter that more evaporation will cause the droplets to decrease in size due to a longer time scale. However, the equivalent instability is also smaller, and this results in smaller droplets forming because the fingers are smaller. So on to the next one, the spinning constant. The opponent put a spinning constant, which he thought very different equations. And the reporter said that the spinning constant is constant and the maximum radius is 1. And in this case, I partially agree with the author. Though the spinning constant does not change according to the reporter in the experiments, this spinning constant actually reduces the predicted power of the theory. And so the last one is simultaneous characterization. In this case, I agree with the reporter. The temperature values, since he used fluids to the ones that were used in the papers. And in this case, I believe that since these are liquids, the surface value should be similar. So the reporter gave unsatisfactory interpretation of the phenomenon and attempted on the phenomenon using proportionality, and a program question out the screening parameters and unsatisfactory explanation. And in conclusion, I believe the report was not fully answered. Thank you.
Thank you very much. Concluding remarks of the reporter, please.
So one concern of the report was that there were some inconsistencies with the shape of our droplets and also how they look like. This is due to the random perturbations which can occur. And also, to go to slide 26, we mentioned again that there's some limit where I think we can predict what actually happens, but I think for the scope or the magnitude of stuff that we investigated, this is sufficient. Then also, the reviewer pointed out that I did not explain well enough what the critical concentration phi C is. The critical concentration phi C is the value of the alcohol component where the evaporation significantly decreases of the mixture. And what this leads to is that when you place a droplet with a concentration that's lower than the critical value, it will no longer spread, as you can see on slide 27. And what we also did is we predicted this. So if we go to values like let's say at 0.2, we do not see the phenomenon because the surface tension can hold the droplet, it's constituted. And I think the reviewer did not understand that it is the gravity that actually forces this to overcome. But if the surface tension is high enough, that we can constitute the droplet and the phenomenon does not occur. Furthermore, I would like to say that we have two references for the critical mass fraction phi C. So this investigation, also on slide 30, where we have our capillary length, and you can see that the vertical asymptote defines the critical value phi C. Furthermore, the opponent said that I had too much of a focus on the wonder droplet, so if we go back to the task set on slide 2, it specifically says to investigate the parameters that affect the fragmentation. And I think that to investigate this, we have to know the conditions for fragmentation to occur. So that is why the wonder droplet occurs. If we have too low concentration, it doesn't occur. If we do not have any oil left, it doesn't occur.
Okay.
The evaporators, and that's why our task is good. Thank you.
Okay. That was a long last sentence. Okay, now we'll have time for questions. So please can both for all reporter, opponent, reviewer come to the stage. Can we have one mic or maybe even two going down to the jury? And please, jury members. Mikhail was first, then Mihaly. Okay, Veronica, can we have the mics, please? Mikhail first.
Okay, to the reporter, what the theoretical slides you had, usually in the bottom corner you had like your reference. Can you quickly clarify whether like all the formulas you use can be found in those references, or if you use them as a base and build on top of it?
So basically, our main proportionality on slide 12, this is given by literature 12. Yeah. So this is given by literature. However, what is missing is the derivation, also the assumptions of this formula, which we had to, I guess, reconstruct and see what exactly can be assumed and why this is true.
Okay, thank you, Mihaly.
Okay, then could you go to slide number 34, please? To the distribution. Just a very short question. Do you have any theoretical background for this or idea behind this distribution for the droplet size?
No, we do not.
Okay, that was quick.
I would like to ask the reviewer, so why do you believe that viscosity should be important in the equation for lambda C? Why do you believe there should be viscosity in the equation for the critical wavelength lambda C that you asked the reporter?
Because the reporter mentioned in his report that the instability is caused by the difference in viscosity between the two fluids. However, in these equations, you do not have any viscosity term, and I believe that this is incorrect, given this quadratic explanation for the instability.
Okay, thank you. Does the reporter agree with this?
No, I do not agree, because the difference in viscosity is the condition for it to initially form, but then the governing properties of the dimension, the length dimension, the dimension of the capillary length is not governed like this. So it's just the initial condition.
Okay, thank you, Karen. Yeah, so I have a question for the reporter. Do you think it will be possible to experimentally measure the thickness of the grid of the ball?
Yes, we can use laser interferometry, so it's like 74. Unfortunately, we do not have access to this, but this is how we measure the depth of your drop.
Okay, thank you. Can I have the slide number 8, I believe? So you speak here about solid liquids and solid gas interface, so where is the solids here?
Sorry, so this is just Young's, sorry. This is Young's equation, but so I specifically said that oil is not a solid, and it actually shears, which then ensure that the contact angle is...
Here solid means what?
No, we first say that it's a solid, but then we distinguish the case that it's not a solid and it can shear actually, which causes the instability.
All right, another question to the reporter. On slide 31 and 32, you show these proportionalities.
Yes.
Did you ever actually measure those? Like, do you have some quantitative or only these qualitative comparisons with the pictures?
This is a qualitative comparison.
Yeah, you do not have a quantitative one?
No.
All right, thank you.
Okay. Peter?
Thank you. So you mentioned in your question, you mentioned in your question that the reporter should actually read out an operation, but if we there is no operation at all.
Yes, use the microphone. You can answer this question.
Okay, so without evaporation, the phenomenon wouldn't occur, and changing evaporation rate changes the phenomenon. However, without evaporation, we could check if the submaterial instability really causes the fingering. And the
Okay, thank you.
Sorry, my opinion on this.
Yes.
Oh, so I agree that we do not see the phenomenon, and basically our droplet, if the initial IPMS value is higher than the critical value, it will just be part of that.
Okay, thank you very much. I'll give some extra time because at the beginning we had technical issues. Natalia?
So are you able to get the value for theta C from your theory for the critical concentration? Does your theory relate to it somehow? And
Yes,
if you compare it, does it agree?
Yes, it agrees. So if you go to slide 27, my theory predicts that this x-axis intercept. So
all right.
It's the x, and also our capillary. So if we go to the capillary, slide 30.
Okay.
This is the vertical asymptote.
Okay, so Sharon?
So I have a question for the reporter. So can you qualitatively explain why an isopropanol and although they're like chemically similar, but we prefer to use isopropanol?
This is something to do with the interactions and how easily it can evaporate. So in chemical, I think ethanol is slightly bigger than isopropanol, but isopropanol therefore can also evaporate.
I will have a very, very good question today. All this graph, like so much. So basically, my question, let's say, if we would focus on, say, the beginning, would you say how it fits, or let's say this part because they are different? What would you say? Why does it really fit on the same?
Because one specific measurement to improve this, then taking the standard deviation of the measurements, but this was not done.
Okay, so
these points
have significant errors here. Okay. Thank you very much. That was it. That was the time. Now the jury has it. Thank you very much. Good degree. For the jury, the important message is that the only thing what counts what's happening. What it counts for you as jurors is the relative rating. So whatever you set for the starting is something you have to rely on. So I don't interfere in any way with your gradings, but like starting with an extreme grade like 1 or 10, round might cause you troubles to adjust for the next round. Within your grading selection files, you would aim on having an extreme grade now. You might consider a little bit and keep space for the next round sides. So going both up and down. But still, of course, it's your individual decision on grading. For those familiar with IYPT, we will show the grades of all the jurors here and now, and one of the highest and one of the lowest grade for each stage will be explained by the respective juror using the partial grading score sheet. The juror has now hard to fill in a pretty complicated table with different partial grades, and then use this to justify their decision within the grading. I also have the same task now, so I'll be back for a minute to finalize my work, and then I'll be here. Some are still working.
You can start. You can start anytime.
Here's the last. We have scored. Because in many of the national competitions, we even go like do not show a bit more attention for the closing ceremony, but according to the IYPT,
we need to show the grade. Lead the jury members to and to get changed. Which is almost impossible to get. And maybe at some point we'll be able to agree that we don't show it. Anyways. Show. So I'll read them starting from jury and then so grade for the report. Now 8, 7, 7, 8, 8. Grade for the opponent. Now 7, 7, 7, 8, 7, 6, 6, 6. And a grade for the no 7, 7, 7, 7, 7, 9, 6, 6. Assistants to give me the sheet with the grade so that I need it now. I know you need it also, but we have some more time. Yeah, okay, sure. No, this is perfectly fine. We don't need to have the official. For this report, we just had 8 and 7, so I try on a voluntary basis, so would like to come. It's like in the school, if no one had, I'll call someone, so you have a chance. Easier, Mihai. You will be back with the 9 anyway, but. Okay, and your partial grades?
1 at the beginning, because it's already here. So for this, and especially with the opponent, 1.5.
Okay, thank you very much. And one of the lower side, Kevin?
Yeah, so my grades. I was 1.5 and then 1.2, so not quite as generous. 0 for that too. So
yeah, like the partial grades are very similar. It's just kind of a rounding error or a rounding expression. Let's go to the. So basically, two main partial grades are 1, 2, and 1.1, and then round it up. Because all in all, okay. 2 major points from my point of view. The first one, I really liked proper prioritization in the sense that you really mentioned a lot. And again, mixing the really important, the one which is not important, and for, at least from my point of view, for gaining more points, you need to show us that you know what is really important. And basically the other general thing from my higher concentration on what was not done, rather than on what was done. So of course, for every think about many other aspects, many other parameters, many other theories, other instabilities, whatever. But unless it's a critical thing, then it's much better on the topic which was really presented and focused on in the presentation. But again, it was like the differences were not wide. They were 4 6 4 7s and a single 8. So Sharon.
So I gave a rank of 8, so I guess I can say my partial scores first. So 1 in the beginning, and then the question, 2.5 for the speech, the discussion, and that 8. So questions that you asked were actually quite like mass concentration, how to use to color it. So like I think these are like good like short questions that are really important to the experimental aspect of this problem. I also felt like you started the discussion quite well with just the first principle. Although like during the discussion you did have a little bit of a detour into like the asymmetry, which I personally thought was like something that might just be like the way that you dropped the droplet. But at the end you finished off with love particular graphs, which I thought were very good. I think this is what a physicist should do.
Okay, thank you very much. Now we proceed to the reviewer. We had 2 6s on the lower side. Natalia, may I ask you to comment on that?
Yes. My target grades were 1.5 questions, 1.25 for review of the report, review of position, and 1 analysis. Your questions. So I would like that you pointed out the 10 meter per second spread velocity, which a number from opponents questions that opponent really noticed the did, so I really liked it. And I also like your question on scale you recorded to show us, next slide. Hopefully that topic was very interesting. However, I did not agree with your opinion on the C, and I rather agree with the answer of the reporter that he gave in the jury questions. And I also felt like the review of the position was a bit too short. And in the content, you mentioned what you wanted to see there, and the opponent kind of didn't address. So I could have been elaborated. Yeah, and I actually did like your point.
Okay, thank you very much. And Mihai?
Just, I would have said
here while I was explaining, it only got you the stage, so that's fine. You good answer.
The explanation will be more or less the same, but which is obviously already sufficient. I really like the questions, 1.5 of the questions. I've seen 2.5 for the review of the report and 1.5 for the review of the opposition. And actually I like the discussion and I like this. Obviously I cannot decide right now which one of you had right in the special case, but I think that it's, I'm just not a specialist of this area, but I really like that you have a point of view of it. We'll discuss it about at least 1 hour long, and maybe can decide which one of you has right, but you didn't have the time for that. And third point again, 0. It's actually 8.5. Obviously, 8 or is it better than 9? But the teacher again, I've seen you before in the 2 and 1, maybe like twice, and I could say that the Singapore team had made a progress. Somewhat slower and some I really appreciate it. That's why
Okay. Thank you very much. I still have to comment on that. Seen the same presentation from the Swiss team. I don't know, the second round or second fight or so, and from the jury goes like, guys, it's really like the speed you have after like 10 seconds. Could you please slow down? And they said like, no, otherwise I don't manage it. I also see really letting out a big portion of the presentation for you, and having a very nice presentation here with all the masterclass in the appendix. So I have to say that we also see that like the progress within the tournament, within the teams is really huge. And if we just would run now a different tournament, it would be much higher with all the presentations that they did and the lessons there. Okay, anyway, thanks you for the stage. Let's make, I know they're making, but we need to be efficient, so let's make a 10 minutes break, go to the restroom, do it, and we'll... Thank you very much.
Scold them. I'm going to go and talk.
I got already some messages that like, yeah, we are online. Microphone feedback is ready. Okay, so now we're continuing to the second stage of the final physics part. That means that the same continue but in different roles. So now the reporting team gets a bit of rest by acting as a reviewer. That's, by the way how I do remember which is the direction of the rotation, that the reporter needs to have some rest afterwards, so he returns to be the reviewer. And we have the former opponent now as the reporter, the team from Poland, and the former reviewer in the position of the opponent from Singapore. In the selection fight, most of the selection fight, the opposing team would challenge the reporting team, but he will to see the best what the students have, and that's why since a long time ago we allow the teams to select the program. None of you would remember that in the past it was even the final was the challenge with some limited number of programs, so it might have happened that even the best programs would not be a limited number. You don't really have to. Okay, people are still streaming into like to finish because at 1 minute we have to finish and start the 5 minutes preparation time for the reporter. Whenever you're ready, just tell me and we will start.
I'm gonna turn the camera around and face us.
After you win.
What's that one? It's okay, don't worry, it's okay. It's alright.
Az elmondott a gondolító, megráztam magam, amit te.
Oh my god.
I think welcome, ladies and gentlemen. My name is Untitled Chapter and I represent Team Poland. Today I will show you our solution to problem number 8, equivalential lines. So in this problem we need to place 2 electrodes in water, supply the same voltage, and then use a voltmeter to determine electric potential at various locations. We need to investigate how the measured equivalential lines deviate from our expectations for different conditions and liquids. So first of all, when we place our 2 electrodes in water and supply, then we can measure the values of potential by changing the position of our voltmeter probe. And you can see that the potential distributes over the So when we place our 2 electrodes into water and then supply it, there will be some distribution of potential, and we will measure as C. So first we start with measuring for various liquids, and we notice that for the such as rapeseed oil, the values of voltmeter were all. And this is from this we get the conclusion that the liquid needs to be. So what is that? This is because the voltmeter is in fact a very sensitive ammeter connected in series with high resistor. So we in fact need for the liquid to be conducting. In the case of metals, the conductivity is due to the existence of electrons or holes in the metal. But that there need to be some ions. In water, those CO plus and OH minus, and that would be the charge carriers. And in the case of dissociate and many other substances into ions, and those would be also the charge carriers here. So we need to we know that
and we can use the Maxwell Faraday equation to voltage as such by assuming that condensing current is linearly dependent to electric field using Ohm equation and applying the conservation of charge in the equation after some the equation for the distribution of potential in the liquid, which is the Laplace equation. We need to implement our boundary conditions into the system, and we will assume that the most important boundary condition is that on the electrons there is a positive voltage, and we will neglect volts, which means that the value of potential is equal to 0. So we can solve our equation to find the distribution of potential in the liquid. And you can see those values in position, and you can notice that those values of those lines for potential value, for constant value of potential, are equipotential lines. So now we can proceed to our. We created a setup that has of potential at various positions. So we did it by supplying our 6 probes and connecting it with the plate to measure the value at different time steps. Then we connect into the construction that was then connected to the 3D printer. So now our 3D printer was programmed to change its Y position slightly and measure values of potential. This allows us to measure the values of the position liquid. So we can see that when we increase the time of our consecutive equipotential lines appear, control volume of the box and measure the equipotential lines at different positions. Then, after smoothing all of our measurements using average, we obtain from roughly 85,000 and 84,000, we obtain those really nice equipotential. So we can now compare our values of our equipotential lines, and we can see here that those smooth lines are theoretical predictions from our theory. So you can see here that 2 volts, and our measured equipotential lines is this small sphere around an electron, but our theory is at the center of the box. When we increase the, we can see that there is some curvature measured, but our theory is there's also slight bit. And why is that? This is because we did not include the creation of ions, because we know that ions must be present to conduct a carrier through water. So let's analyze what happens. In the case of anode, we need to absorb electrons. In case of H3O+. So that would be the respective chemical reactions, and in the case of cathode, we need to emit electrons and oxidate H+, so that would be the respective reactions. And now we know that creation of those ions costs some energy, and this would create a jump in the value of potential, and we can find using a Nernst equation for each respective reaction, and with this of potential at cathode and anode. We apply 5 volts. In fact, we are applying 1.5 on one electron and 4.17 on the other. And now our prediction is much well predicted. This is that the consecutive pretty close to each other for the different values. But how to analyze those deviations? We had to introduce a fact the difference between experiment and theory for each measured position, and we come at the whole spectrum of our box. And we can see here that in the case of the near the wall, it is either high or very low. So this means that our predictions deviate near the walls. So this includes also affects capacitance. This means that due to the electricity that electric, we need to include that there will be some bound surface charge on the walls. To analyze this surface charge, we can use Gauss law in the electric to obtain a very simple boundary condition for the potential value. That we are neglecting here the charge on the walls, because it is very small. And with this, we can find a simple boundary condition between the water and air. So to solve such a Laplace equation with such a complicated boundary condition method, and we use to the software PEM for 2. And please notice that there is also a box for the, because we need to also find the distribution of the voltage in air to make sure that water-air boundary condition is correct. And now we can see in our solution the interested region of water, and we can see here that on the wall our boundary condition holds because the water is much higher than the permittivity of air. So now we can compare our finite element method. And we can see here that the field is very good. So now let's distribution of values of error, and we can see here that there is a movement, especially in the region near the walls. So here is our comparison with theory using finite with analytical theory neglecting the walls. And please notice that they differ, but we need to introduce some value that would allow us to specify how much our theory is better. So we introduce root mean square as a mean square root of error square, and that our predictions in finite element method are at least predictions using the analytical theory. So now let's look more deeply into some deviations that can occur, because we can see here that from the experiments. And let's look at the cross section of our measurement and comparison. We can see here that at the region there is slight deviation, but our measurement is still inside the uncertainty. But because of a very low gradients of the position of equipotential lines might deviate a little bit. So now let's proceed with our experiment. In our experiments, we measure different distances between electrons, and please notice that for all of our experiments, we use demineralized water. So for different distances between electrons, we can square, and we can compare different distances between electrons, and we can find that all of our measurements theory fit very well to be measured. There are no parameters fitted in each of our. In the case of electrons really close to each other, we can see deviations and a little increase in the value of the mean square. So let's analyze, let's get more deeper view in the cross section of such a case. See here that there are still some deviation. There's some deviation between theory and experiments. But our theory is still nearly inside the electrodes, and for very small values of voltage supplied to the electrodes, the effective voltage, you can find that the theory and experiments increases due to the fact that gradients are very low, and we cannot predict those gradients. So in the case of, we can see that our is pretty well predicted. And we can move to measuring different distances between. Unfortunately, our experiment has its limitations. Greatly those different limits. For all of our previously we analyzed different kinds, especially those. So we decided to now add some salt into our demineralized water. And you can see here that when we increase the amount of salt, there's a movement of electrons, and this is the same thing we noticed earlier when we neglected the n space. So we can compare root mean square value to different amount of salt. This is the root mean square value for element method and the neglected wall theory. And please notice that each of our measurements contains 1,000 measurement points. The theory and experiments, and you can see here that there are very huge values of the root mean square error, and let's analyze what's happening. In this case, we can see that at the cathode there's an emission of a huge amount of hydrogen, but the amount of oxygen is really small. So this means that there is some reaction occurring at the which could be the oxidation of the electron other things. And let's look at there's also the surface of the
What was the definition of your ideal case of the equipotential line?
Ideal case for the equipotential line? Yes. Okay, so it's a line at which the constant value of potential is distributed.
And what are the so-called ideal lines that you define?
I don't understand the question.
What is the value of the current that is passing through the water?
It's very small because the amount, the conductivity, the resistivity of water is of the order of conductivity of copper times 10 to the minus 8.
Can you check what is the order of magnitude of this current? The order of magnitude of the current.
Okay, so it would be 10 to minus 4.
Okay. So which group is not green? Sorry? Yes. In this picture, I can see that the electrodes are not straight. Is this?
It's just a phenomenon presentation. We are asked to place two electrodes into water and supply a voltage and then measure the position of
Are you ready on experiments? Did you ensure that the electrodes are actually straight?
Yes, of course. You can see this on our slides with experiments. And here you can see that our electrodes
Thank you very much. We still have time for discussion. Questions now. Payments for preparation of the proposal, please. Okay. The time preparation is up. Please start your position.
Good morning. Today I will be opposing problem A. Select equipotential line. In summary, the reporter has constructed a setup consisting of conducting electrolyte and electrodes and made use of a robotic mechanism to measure the potential reading. The reporter has also used the class equation and the Nernst-Planck equation as well as the finite element method to model the potential in the electrode, as well as introducing a value of error to measure the deviation from the ideal case. Firstly, I'll touch on some of the strengths of this report. Firstly, the reporter has made use of salt water and copper electrodes to carry out his experiments. And this allows him to better observe the phenomenon, since a conductive liquid is needed for his setup. Next, the reporter has also demonstrated the deviation between the ideal and measured equipotential lines for various conditions and liquids. He has introduced a value of error to measure the deviation and make use of the through means by error. I believe that this is commendable since it allows the reporter to be able to quantify the deviation between the ideal case in his experiments. Next, the reporter has also made use of a robotic setup to accurately measure the voltage reading. And I believe that this is commendable since this allows the reporter to efficiently measure the voltage reading with a very small spacing. Next, the reporter has also accounted for all effects using the finite element method, and I believe that this is commendable since this allows him to account for the walls of the container. Next, and which can significantly affect the potential lines, which he has shown inside this presentation. Next, the reporter has also considered the effective voltage due to electrolysis, and I believe that this is also good because it allows the equal potential lines to be more accurate. However, the reporter still has several areas of improvement. Firstly, his theory has poor predictive power, and there are still shown to be significant deviations between his experiment and his theory, and these deviations are also not qualitatively explained. Next, the reporter has also had a large experimental error, and as you can see in the slides, since the equal potential lines are unequal, it is important that he is able to get more accurate experimental results, since the equal potential lines is the main phenomenon that we are investigating here. So it's important that he is able to measure these accurately. Next, the reporter has also has several simplifying assumptions, and he has not considered the diffusion of ions within the solution, as well as the deposition and time dependence of the equal potential line, which I believe may occur because, as the reporter mentioned, there is some deposition of insoluble salt on the copper electrodes, which may in fact increase the resistance of the electrode on one side, and as a result lead to a reduction in the voltage of the electrode due to the higher conductivity. Next, the reporter has also neglected the time dependence of the equal potential lines in the measurement of his measurement of the lines, since it takes a long time for his setup to fully measure the equal potential lines across the entire container. And as a result, this could have affected his results and contributed to the deviation between the ideal case and the experimental results. Next, the reporter also has poor experimental control, as in his theory, while he has assumed that the electrode is a perfect cylinder, in his experiments can be seen clearly from the video that the electrode is deformed, and this will actually affect the equal potential lines. This changes the surface in which the ions are transmitted from the battery or from power supply to the liquid. Finally, the reporter also has a limited experimental scope, as he has not really varied the rod geometry, which I believe can be done easily by changing the electrodes or the container, and he has also not really varied the container geometry, which I believe he can do by rotating the container. Now, I would like to invite the reporter up for this discussion.
Okay, thank you very much. Now we have 10 minutes for the discussion. If the opponent uses the handheld microphone and the reporter the fixed microphone.
First of all, I would like to ask you, where do I need to include the diffusion? Because you said that we neglected the diffusion, you stated that we neglected the diffusion, and this could affect our potential lines. So please look at our theoretical predictions and say in which moment did we neglect the diffusion? We only assume that there is a steady state, that there is an open equation.
This is a concentration gradient which you have included in the Nussbaum equation, and I did not see the diffusion term within that equation.
But where am I neglecting?
In the interest of time, can I move on to my first point?
Please tell me, where do I neglect the diffusion? Because you stated that very clearly. Where is the neglection of diffusion here?
In here, because this only models the voltage distribution, but it's not.
No, it doesn't. It is not only modeling the voltage distribution. It's modeling the current density in the liquid. Here you can see that from the current density in the liquid, we can arrive with Laplace equation for the voltage, but we are including diffusivity.
I believe that in this equation, this does not actually account for the diffusion of ions.
Okay, I don't agree with the opponent because here we can clearly see that we are analyzing the current inside the water, and then this current is changing into the voltage due to steady state assumption.
Can you let me finish my point first? Okay. So basically in this equation, what you're modeling is the distribution of voltage within this system. However, the diffusion of ions is when, for example, in some region of this container, there will be some ions here. And then and over time, this ions will diffuse out like this, assuming that there is like no voltage or anything.
Yes, and this is the ionic current, which is J on our equations, and we can reduce this J by a spin ohm equation. You stated that ohm equation is not holding in our liquid.
No, as in like if you simply consider the fact that there is just no voltage and no current, and there's just some ions that there's a high concentration in one area, these ions will be diffusing across the liquid. And
yes, and they will be diffusing across the liquid because there will be the electric created, and that, due to our equation, would create the current density in the water, which we analyzed and investigated in our theory.
I believe we have reached a disagreement, since I believe that this comes to, in fact, be accounted for using the different equation where you have a diffusion constant multiplied by the concentration of the ions at that point, and the gradient of the concentration across like center of this.
Okay, so this is affecting the sigma value here, but hence sigma value is
But hence sigma value is some constant for all liquid. We can neglect it and focus as a topic material and arrive to the last question.
In the interest of time, I would like to move on. So now I would like to discuss the effect of the electrolysis. So could you go to slide 38? 38. Yes, in this slide we can firstly see that the equal potential lines are quite noisy. So it's clear there's some.
Yes, this is due to the fact that we are dividing. To obtain correct to obtain those potential lines, we set the maximal value of potential pressure and the minimal value of potential pressure divided by the amount of every potential lines we want to show on our plot, and then show the corresponding values and factor running through the plot. And this loneliness is due to the low gradients of the potential, because the effective voltage is really small. So the loneliness, if you would decrease the amount of potential line, you'll get those lines curves. But this is not the problem.
Do you believe that the waviness of these lines put in state because, because the way that you're set up is measuring the equal potential line? So if I have a container here, it begins by an extrusion across like this.
Yes.
Right. So basically, you can see that perhaps it's because these equal potential lines are changing with time because of the deposition of insoluble salts on the electrode. And as a result, when it is moving and moving this way and it's moving back, it's not actually measuring the equal potential lines at the same time.
Point. It's not that this is measurement for the demineralized water. So the only ions that are created here are OH minus and H3O plus. So there is no time dependency that we created here due to the fact that there are no ions in water. But if you look on the case with salt, there could be in fact time dependency because the reactions that you get the cathode and electrodes are not really normal in fact. And there are values that create, and in fact when we add salt to our solution, there's still the statistic is not holding.
Okay, so I think the reporter and I have reached the agreement that, I agree with the reporter now that because for that graph it is demineralized water, it would make sense that the waviness wouldn't be due to the time dependence of the equal potential lines, since there wouldn't really be jet position on the okay, so now can I discuss about this? We can discuss about this now. So here you can see there's a significant number of bubbles here, right?
Yes.
So do you have an equal potential lines for this, for specifically this case, when there's significant amount of
for example, this plot here. Oh, there's a mistake. Okay, so it's 8. Sorry. The fact of slide is wrong. There's 0.08% plus friction.
So can I clarify that these wavy lines is in fact the equal potential lines measured by your setup?
Yes, and this you can see that clearly steady state is not holding here because of the fact that there are ions present in the liquid.
Can I check why, here, you actually can see that the electric equal potential lines don't even really circle around your electrode. Yes. I believe it's the orange dot, right?
Yes, right.
Do you believe that this is actually because the equal potential lines, as I previously mentioned, would be changing with time?
Yes, this is the case when the steady state assumption is not holding. And this is one of the main causes why the deviation between our theory and prediction is increasing when we increasing the amount of salt in the water.
So I believe that this deviation is caused by the significant bubbling as well as deposition. Would you agree?
Yes. It is clearly steady state is not holding here.
So if we just consider at a certain point in time, what do you believe that the equal potential lines would actually look like at how big?
When there could be measure each potential line at the same time, right? Okay, so I believe that this asymmetry would hold So there will be still asymmetry because there will be some different jumps of values of potentials. But I can see that for a step measurement, for each position, there will be some potential line distributed over.
Would you agree that you think that the equipotential lines will be like split to one side? Because, for example, because of the deposition in bubble, this would reduce the voltage of one of them.
Yes, I agree. The reaction, for example, cathode would in this case decrease the amount of voltage that we need to pay to create a current inside.
In addition, like I have one suggestion for how you could actually investigate the time dependence of these equipotential lines. So perhaps what you could have done is that, like if this is your container, you could start multiple probes inside, and then what you would do from here is that for each of these probes, you would just measure the voltage as it changes with time.
Yes, but that would allow me to measure the equipotential lines. Because I need to find the value, the constant value of potential, and how it is distributing over the surface.
But perhaps you could at least allow you to measure the voltage across like one axis. For example, across the x-axis, then you will be able to see something like this. And then
yes, here we can see this on our measurement, so we analyze the deviation. Okay, so here you can see that for this case, when we analyze the cross section, it is fitting very well for experiments, but this is not what the content requires us to do. So we tried to focus on the position of potential lines.
So in conclusion, I'm appreciative on how the reporter could have measured the qualitative explanation for the deviation of his equipotential lines when the concentration of salt is high, as well as a possible way to measure the time dependence of his equipotential lines. So now can I discuss about the internal resistance of the voltmeter?
Yes, sure. Okay, so let me read the values because I got you some values. So the internal resistance of the voltmeter in the Arduino plate is like so it's like definitely 9.
Okay, guys, I'm afraid. Alright. Sorry for that. 1 minute. So, in conclusion, the report discussed the neglection of the diffusion term within this Nernst equation, and we have reached a disagreement, and I believe that the Laplace equation does not actually take into account the diffusion of ions when there is a concentration gradient. We have also discussed the reason for the deviation of the equipotential lines in the case that there is a significant amount of salt in the solution. And we have reached an agreement that this could be due to the time dependence of the equipotential lines, since there is a significant amount of bubbling, as well as a significant amount of deposition on the electrodes. And finally, we have briefly discussed the internal resistance of the voltmeter. And I believe that this could be significant since for demineralized water, the current value is actually quite low. So in conclusion, while I believe the reporter has provided a good overview of this problem due to the neglection of the diffusion term, and I believe the reporter has not fully answered this problem, the problem statement. Thank you.
Slide 9, please, the reporter. 9. And while you're at that, am I right here in saying that V is equal to the potential?
Yes, V here is the potential, right?
Okay, thank you for that. Coming to your setup, how can you give me an estimate of how fast your motor or like your machine moves?
Yes, sure.
So how long approximately does it take?
Okay, so here you can see the actual velocity of my setup, and then we increase the velocity to show you just that we
Okay, so how long approximately does it take to complete the entire?
So it goes like, you can see here, it's like 30 seconds to go through one side to the other.
Okay, thank you. To the opponent, do you think that the voltage here is strong enough to cause electrolysis?
In this graph?
No, when salt water was used with like the higher voltage range, do you think it's high enough to cause electrolysis?
Yes, I believe that even at a low voltage of 2 volts, for example, if the concentration of the salt within the solution is sufficiently high, electrolysis can occur.
How high was the concentration of the salt? How high was the concentration? Yes.
Okay. So you can see here that we variate very different amounts of salt. So the maximal one was 0.5% of the mass.
Okay, thank you very much. Coming to the boundary conditions, what boundary conditions were used here? Because that wasn't explained.
So in our finite element theory, that will be about here. Okay, so the boundary conditions
No, for the earlier theory, I think.
Where?
For the earlier theory, what were the boundary conditions that you used?
For this theory or the previous one?
The previous one.
Okay, so for the previous one, the values of potential were 0 at the infinity, and the values of potential at the electrodes were plus half of the potential light and minus half.
Thank you very much. Does the opponent agree that these are the correct boundary conditions?
For which theory again? Sorry.
Yeah, for the one you mentioned.
The previous one.
Oh, the previous one. I think that if you are neglecting the effects of the walls, those boundary conditions should be correct.
To the reporter, how does the simulation relate to our experiment, and what physics contributions does it make? It seems like we're just pressing some buttons and making a simulation.
So see, we cannot find analytical solution for the Laplace equation with such a bond barrier. This finite element method numerical solution allows us to apply this bond. The only thing we changed from our analytical solution to the numerical one was applying this bond barrier condition.
Thank you. And a final question to the opponent.
Sorry.
And I'll be reviewing Connie equivalence line. This is the task statement. And the particular thing about this task statement is to look at the deviations, especially from what we expect in the theory, so that's what we need to know. Moving on to the outline of the report, we thought the introduction was fine. Some of the problems that I see with this report are the relevance, for example, of the PEM simulation. I don't think the reporter was able to give me a satisfactory enough answer on the relevance and how we can use that, as well as some of the setup issues and qualitatively explaining the deviations from the model. I thought that was lacking as pointed out as well by the opposition. Coming to the strengths and weaknesses of the report. In general, we thought that the setup was well done by using this motor and being able to pretty much scan through the entire water area. There was also controlled flow measurement with mention of internal resistance, and there was some error discussion, so getting into the deviation from our theory. However, some of the weaknesses that we saw with the theory was that without justification, the reporter seemed to assume that each 2D cross-section of the liquid has the exact same distribution of potential. We think is sometimes maybe not justified, especially with the mixing of this machine. We did not see particularly the relevance, or it was not well explained how the FEM simulation is particularly relevant, and it was also unclear whether this is 2D or 3D. I assume 2D. On slide 9, we actually saw an issue with one of the formulas, being that the electric field should be the negative gradient of the potential. It was actually wrong in the report. And there was some explanation of electrolysis. There were also the deviation was one of the major problems that I had. So explaining why the potential lines near the electrodes are so far away from our theoretical predictions. Using a lot of graphs, that was the case. And also some of the things that weren't considered were the damaging effect that salt can have on these electrodes, and I think over time the salt will almost corrode them and indeed damage them. Furthermore, the depth of the water was not very as up to the parameters that have been discussed. Coming to the opponent's speech summary, we agree with the opponent that the theory has poor predictive power because there are huge deviations. Of course, the task mentions this, but I think this could have been easily improved. Also, the time dependency, so how the potential lines change over time, was not considered at all, especially with the long time frame of the machine used. To the opposition, they correctly pointed out certain points, for example, the time dependency, as you mentioned, is also large error. However, they did question some of the actual main points that I felt were missing, which were the relevance of the FEM simulation and also the boundary conditions, which I have to ask about. They also talked about electrolysis for a while, although I think in most cases the voltage will be too small to cause electrolysis in this case. In general, also at the beginning, the reporter seemed to lead the discussion. Now coming to the discussion topics, they discussed the ionic flux potential, and the reporter thought that this was a complete model. However, we agree with the opponent because we think ion diffusion should have been considered by the model. The next topic was the electrolysis and also the wobbliness. The opponent thought that it came from the robotic setup. However, we agree actually with the reporter because we think the voltage gradient was very low, which caused large deviation. Furthermore, one of the topics of discussion was the bubbles, and we think they were actually kind of speaking past each other, and I agree with both of them. They essentially both stated the same thing. And the equipotential lines being to one side and having the deviations here, we also agree with both the opponent and the reporter. Thank you very much.
Thank you. Okay, we are assuming 2D because our probes are measuring values of potential in the whole container. So the only effect that is changing the 2D assumptions are from the below and top of the water, and these are very small areas in respect to the whole height of the box. So also I would like to say that my use of finite element method was to check whether the fact that the water is dielectric is important to the problem. And if I compare my theoretical predictions with including wall as the water is dielectric or not, we can see that in fact this is the main source of the deviation between the theory and predictions in the case of water. So I would like to say more about the assumptions of in the case of the added salt, we can see clearly that there are increase of deviations between theory and experiments. And I think I will manage to explain very deeply why those deviations occur. I analyzed all of my assumptions and stated why they are wrong and how are they changing the distribution of potential. So there was also an report. I truly made a mistake in the potential definition, but if you look at the equations, this minus will neglect with 0. So in this case, it is not important for this whole equation. And I would like to say that the only thing that diffusivity will change in this equation is the isotropic material assumption. If you would in fact get the lattice equation from just Maxwell equations, then you wouldn't include the ions affecting the current. But we included how ions are affecting the current, and we just assumed that the whole state is isotropic. So this is where the diffusivity might change our prediction.
Okay, thank you very much. Before we start the talk, can I kindly ask reporter or one of the viewer to come to the stage? They have to share one mic or you just standing by. And I'd like to welcome the jurors to pose the questions. Natalia was the quickest one this time, followed by Mihai.
Thank you. Can you please turn to slide 30 or 32? Maybe start with 30. So I feel like there is a systematic shift between the experiment and the theory. Can you comment on this? Was there systematic deviations?
Yes. So I believe you're asking about the areas near the electrodes, right?
No, I'm asking about all of them. And if you turn to slide 32, all of the error is on one direction. Everything is green, so it means it's all either positive or either negative.
Okay, so I believe this is all of our experiments have no fitted parameters. So I believe this is caused that there's some different change in the value of potential in the electrode, and this is causing this systematic error. So here we can see that there could be some asymmetry, and this asymmetry is due to the fact that the Nernst equation couldn't provide the excellent prediction for the jumping potential. Okay, thank you very much. Then Mikael and followed by Mihai.
All right, a question to the reporter. You stated that your probes and the electrodes are like fully conductive on their whole area, right?
Yes.
And the review was like, okay, this basically measures like an average of the whole probe, right? And in your concluding remarks, you stated that this will only have an influence, like a small influence, because the top and the bottom is not very important. Did you ever try to like prove this by like isolating parts?
Yeah. Actually, isolating the parts of electrodes would create a great complexity to this problem because there is no current between the isolation, but the voltage.
So did you try it or not?
No, I didn't try this.
Mihai, could you go to slide number 33, please? And open the small graph which is animation.
Yes.
Yeah, this one. What aspects can have an influence on the slope of this theoretical prediction?
What aspects can influence the slope of the prediction? This?
Yes.
Okay, so the difference between the potential, difference between both boundary conditions. Because Laplace equation is holding, and the temperature is only affected by the boundary conditions. Okay, Peter?
Okay, also in the reporter, so am I right that you use in this calculation this fan program?
This red line?
No, in the exponential line. So here, the calculation is based on the fan program.
Yes.
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 And do you know exactly what is behind the calculation of the fan program?
Yes. Okay. So we know that. Yes, I know, because the fan program is creating a mesh of
Okay.
Is it and then Natalia and then Gary.
So to the reporter, what is the voltage of your like negative electrode? Is it positive or negative, like with respect to ground?
Okay, so because we can add the amount of volume of potential as we want, we decided to set the one electrodes to be 0, and it is connected to the ground. And the other one is 5 because the 5 are different values, and this is the jump of voltage in our source.
Okay, thank you. Natalia and Gary.
So did you try to investigate also the case where the height of the liquid is small?
No, we did not.
Okay, thank you. Do the reporter, opponent and reviewer agree that this would be a type of deviation included in the test?
Do you believe what?
The height of the liquid.
So that the type of deviation due to change in height would be the type of deviation that task asks you to investigate?
I think that this is one type of deviation, but
Okay.
I should also.
Does the reviewer?
Yes, I agree with the point. I think this could be a condition.
Gary?
So I want to ask, the electrodes would be able to overlay the most
was the distance between the electron and the bottom?
No, they were not touching the ground, they were like 5 centimeters.
I have one question because the task says that like, you should investigate different liquids. So I know that you investigated very deeply the demineralized water. Then you tried with salt, but you didn't have really your expectation for the salt. So is there any other liquid where you could compare your expectations with your measurements rather other than demineralized water?
For example, compare them with the oil.
And did you done like any other liquid than the demineralized water?
I've done salt, and I made some predictions with using some assumptions, and I will request to ask what mitigations are quite relevant.
Okay, there's a question, Kevin.
To the opponent and the reviewer, you were talking about time dependency. How do you think the actual conductivity of the solution is going to change with time?
Okay.
I believe that because of the electrolysis, the salt within the solution will be turned into in the case of like electrolyzing water, because actually the water inside the solution is going away, so concentration will increase. But in other cases where instead you're electrolyzing the salt, then the concentration of the salt will decrease.
Okay.
Yes, I think that if the salt deposits on the electrodes itself, the conductivity would likely decrease.
Okay, thank you very much. That's it. I just want to comment. I am a bit more relaxed with the time for the questions of the jurors because basically the time is scaled for the usual jury of 5 persons, so roughly 1 minute per juror. Here we have 9 jurors, so I tend to give a little bit more time somehow to get everyone a chance to pose a question. Okay, guys, thank you very much. So as in the previous stage, all the jurors will have to fill in their score sheets. Every stage is getting more complicated because they may now have to compare within this final. So I also go back when I see it at the back once I finish with my work.
Okay, so last check, is the jury ready? Grades for the report. No. 6, 7, 6, 5, 5, 7, 7, 7, 5. Grades for the opponent. No. 7, 6, 6, 7, 6, 6, 6, 8, 7. And grades for the reviewer. No. It's a 7, 6, 6, 7, 7, 7, 8, 8, 7. Thank you very much. So I believe we had a nice presentation. Okay, can I get the paper, please? No, guys, no, I need it now. You have fun. Guys, you don't need the copy now. Like you can do it in 5 minutes. No, it's like we still have next stage to put it into the system. Okay, thank you very much. So you just basically make one copy, you give it to me, I'll give it back, promise, and then you put it into the computer. Okay? So for the report, there were a couple of 5s and a couple of 7s. So maybe on the lower side, I don't know, Shayan, would you comment? You're getting a mic.
Yeah, so I felt like with this problem, the way that this problem is set up is sort of interface of physics and like physical chemistry, and I feel like for the solution that you have done, I feel like it's missing quite a few parts, and I feel like the fact that you have not varied the liquid outside of like water plus salt and oil cause you to miss some important effects. And I just say my part I gave you 3 for the brief report, and then 1 for the discussion, and then the mark off for the questions. And like during the discussion question, I think could have been a little bit more like asked and kind of more like scientific discussion rather than like sit back.
Okay, we had 7s there. So, I don't know, Mikhail? Okay, sorry, thank you.
All right, then to the report. So first of all, my party, for 1, the 4, and the 2. And I think, so primarily, I really like your experimental setup.
Just put the mic closer.
Oh, yeah, sorry. So primarily, I really like your experimental setup, your introduction, what the voltmeter, for example, actually does is very important. Your automated setup actually allows us see like the whole area, which was of course especially important to like experimentally verify the deviations around the edges and stuff like that. And I also think that you did a very well job of like actually fulfilling the task, which specifically states that you can investigate the deviations, and you introduced the error functions to like quantify this. So I really like this one. Your discussion contact was of course a little bit rough, I agree, but in principle you had a very good physical understanding of what happened. You were usually able to support your points very well. So I thought that was very nice. And I think your own contribution to the problem has been significant, and your past fulfillment is also, I think I already stated, quite high. So that's
Okay, so thank you. And for the opponent, we had a couple of grades of 6. So Kevin, would you comment on your 6, please, for the opponent? Keep the mic closer.
I was pleased with the way you started off, but your initial questions were good. but when we got into the speech, some of the relevant points I'm not sure we got through to. And in the discussion with the reporter, I don't think I gained really any extra information. So that's the main area that I marked down. I also thought the time dependency, just the fact that the rate of solution changed, I think it was probably increased rather than decreased.
Okay. So the partial grades?
My partial grades are 1, 1.5, 2.5, 1.5,
Okay, thank you very much. Actually, I also had 6.5, so like, on the other side, I think it was just Mihai, no? Okay, but so the opponent, was it Mihai you gave? No, so we have an error here in that paper, because it was Natalia gave an 8, that's what I remember. So Natalia?
Alright, so I gave you 1.5 for questions, 2.5 for the speech, and 2.5 for the discussion, and basically I really like the points that you brought up. So I did like that you brought up, for example, the time dependent, and that this could be relevant with salty water, the deposition of salt, especially since, as also the reviewer that pointed out, the time to conduct experiments take a longer time. I don't know how much this effect would be, but I thought it's a very good point to address and to discuss. I also like that you brought up the diffusion, and I'm still not sure how or whether they correctly included it in their theory. And I also like that you analyzed in detail the comparison of theory and experiments, for example, on slides 44 and 33. So I basically didn't know how much better. I said that already.
Sorry, I was correcting. Okay, so Mihai, you had a 6?
Yes.
Okay, you don't have to explain, I just like correcting it. Okay, but like, while the microphone is with you, you had an 8 for the reviewer.
I was actually wondering if it's not a 9, because my feeling was that the 2 reviews were basically on the same level, but I realized that the points ended up at an 8, so that's what I'm thinking. I've seen more or less the same. I think the only difference was that yes, I still have the power and time to get something pointed out, and you were just finished with almost just finished with the last evaluation of the last class, even though I really like the discussion analysis which you have.
Okay, so did you state your partial grades?
Oh yeah, sure. Beginning at 1.5 the questions, I think they were really, really good. I do review analysis 2, proposition 4.5, and discussion of analysis also 1.5.
Okay, thank you very much. And Carrie, you had a 6 only?
Not really so different entirely really, but I took a mark off and missed points. I felt that the structure and design of the tank with the long electrodes and things should be looked at, and also the production of bubbles. I've got some questions about that which would have been raised. So I've allotted a 0.5 there, which basically could take it down to a 6. The grades were actually, so there was a 1, 1.3, 1.5, 1.5, 1.5 and minus 1.5.
Okay. Wow. Minus 0.5. Minus 0.5. Okay. I heard 1.5, which would be off the scale. So I just wanted to be sure we stay consistent there. Okay. Thanks for the fight, and let's have a 10 minutes break and get here again. Okay, I give you 1 or 2 more minutes to sit down and cool down. We have a speech then, it's no lunch and dinner. Doesn't seem to be really helpful. I'll think about something else.
Tomika, ha felállsz, ezt meg
Okay. It's here. That's the last fight, last round, and I don't know really, I don't have it in my mind, I guess everyone else has already the points calculated, but I guess this also will be very important for the final result, so it's like, it's not decided yet, so to say. So I'm looking forward for the presentation of the team of Singapore, so can we start your 5 minutes for preparation? Okay, so let's do it 5 minutes for preparation for the team Singapore.
Nagyon jól látszik az így tényleg megvan az a szöget.
Good morning, children. I'm Siri from Singapore. And today,
Sorry, the clock?
Oh, okay. Sorry. Okay, good morning, children. I'm Siri from Singapore. And today I'll be presenting on problem number 3, ring on a rod. The problem statement asks us to investigate the motion of a ring that's spinning on a vertical steel rod, as well as determining its terminal velocity. The relevant parameters for the problem are the relative dimensions of the ring and the rod, and the coefficient of friction between the ring and the rod. Here is my content for today. I'll be presenting my experimental setup, followed by a qualitative account to explain why the ring reaches terminal velocity. I'll then analyze the steady state and transient radius of the ring separately. First, let's take a look at our experimental setup. As you can see, we drop the ring down the vertical steel rod secured on two ends to minimize shaking. Firstly, let us establish our coordinate system. The black arrows denote the lap frame, while the colored arrows denote the body fixed frame, which will rotate with the ring as shown in the videos here. The ring is free to rotate about 3 different axes, namely the tilt, which is the angle between the normal vector of the ring and the z-axis, precession, which is the measure of how much the ring spins around the rod, and the spin, which corresponds to the rotation of the ring about its own center of mass. As such, we place 2 cameras in order to properly observe the motion of the ring. The side camera accurately determines the tilt and position of the ring, while the bottom camera allows us to determine the slant, the precession, and the tilt of the ring. In our experiment, we observe 2 configurations, one where the ring has 1 contact point with the rod, and one where the ring has 2 contact points with the rod. For single contact, we observe oscillatory motion due to the rapid transition between sticking and slipping. On the other hand, terminal velocity is observed only for double contact. Hence, we'll be mainly focusing on double contact for this report. Why then does the ring reach a terminal velocity? As the ring falls down, it hits the rod and generates a normal force. The contact point is a downwards velocity, thus there's kinetic friction which opposes the movement. This kinetic friction causes the ring to rotate, causing the center of mass to be below the contact point. And using the formula for torque, normal force and friction will result in the torque out of the pitch. Considering an angular velocity in the plane of the ring, the initial angular momentum will point in this direction. We see that there must also be a friction force along the plane of the ring opposing its rotation. The torque, caused by the tangential friction, will point perpendicular to the plane of the ring, decreasing its spin. The angular momentum vector will then swing in the direction of the net torque vector, causing the ring to reach double contact eventually. Due to the double contact, there are now 2 normal forces providing centrifugal acceleration. Considering the rotation about the plane of the ring, we find that the kinetic friction will oppose this, causing the spin angular velocity to decrease, while increasing the angular velocity about the rod, until the no-slip conditions at both contact points is satisfied. When the no-slip condition is satisfied, the ring will reach terminal velocity, while the net torque by the contact forces causes the angular momentum vector to precess around in a circle. Now, allow me to discuss the steady state motion of the ring. We begin with the equations of motion. To do so, we can first start by analyzing the relevant degrees of freedom. 1 degree of freedom describes the height of the center of mass of the ring along the rod, and for the orientation of the ring, the 3 degrees of freedom correspond to the Euler angles, namely the spin, tilt, and precession of the ring, which we have previously defined. We can then express the angular velocity, as well as the rate of change of angular momentum, which equates to the net torque, in terms of the Euler angles. Writing Newton's second law, we know that the net force consists of gravity, the contact forces, which is a combination of the normal and friction force, as well as the air drag. We can also write down the no-slip equations in both the tangential and vertical directions for both contact points. And taking count of the center of mass as simplifying, we arrive at this equation, where the term in purple denotes the torque by rolling friction. But due to the symmetry of the double contact configuration and the no-slip nature of both contact points, the system will in fact be underdetermined. Hence, we proceed to examine the no-slip condition further and explore the possibility of solving the equations of motion. To verify no-slipping at the contact points, markings on the ring are tracked using computational pixel counting software. We first track the tangential position of the marking. We see that when marking is in contact with the rod, the tangential velocity is 0. Similarly, the vertical velocity is also 0 at the contact point. And doing the same for the second contact point, we know that there's no vertical and horizontal slipping at both contact points. And this implies that there's no kinetic friction, which is very interesting. As the ring reaches steady state motion, its kinetic energy has to remain constant. And at the same time, the ring is constantly losing gravitational potential energy. In order to keep its kinetic energy constant, energy has to be constantly dissipated through rolling friction and air drag. And it's possible to remove energy gain and energy loss from the system without changing the fundamental physics causing the rotation, which are the contact forces. And experimentally, we also observed that the weight and drag are relatively negligible as compared to the contact forces F1 and F2 due to the high angular velocity of the ring, and can be eliminated from the equation to obtain the steady state tilt angle of the ring. In order to obtain the terminal velocity, we resort to an energy balance. To model drag, we first calculate the velocity of the center of mass by projecting the angular velocity along the instantaneous axis of rotation. We then use the turbulent drag model to model power dissipation. And for rolling friction, we know that we can express the resistive torque in the normal and vertical direction separately and calculate power dissipation using the following equation. And lastly, we balance the power input due to gravity and the power output from energy dissipation to obtain the terminal velocity. Now, let us move on to our experimental verification. First, I'll discuss the tilt of the ring. We know that when there are two contacts, there's a maximum and minimum tilt. We plotted the maximum and minimum tilt of the ring against the ratio of its inner radius to the rod radius. The gray region is where the ring is smaller than the rod, and comparing our data to the theoretical prediction, we see that past a certain point, the theoretical tilt needed at steady state exceeds the maximum tilt. And this critical ratio is denoted as lambda. Below lambda, the ring is unable to achieve steady precession even with an initial spin. And above lambda, the ring is able to reach terminal velocity. Plotting a graph of different outer radii, we know that lambda increases as the outer radius decreases. To qualitatively explain this, we know that a ring with a greater outer radii will have a greater moment of inertia. In order to achieve steady precession, the greater tilt is required to provide more torque. But tilt is constrained by the inner radius. Since the greater inner radius implies a greater range of possible tilt angles, so the required inner radius has to increase as the outer radius increases to allow for steady precession. And here's the phase plot of the ratio of inner radius to the rod radius against the ratio of outer radius to the rod radius. The green region denotes the geometrical conditions required for steady state to be achieved, while the red region denotes the target is impossible to achieve steady precession. And again, we see that the critical boundary increases as the outer radius increases. Now, we'll discuss the terminal velocity of the ring. And this is a position time graph for rings of various sizes. Comparing our theory to experiment, we see that there's a good agreement. Next, we plot a graph of the terminal velocity of the ring against the inner radius of the ring while keeping the outer radius fixed. Below a certain radius ratio, terminal velocity can never be reached as the tilt required is greater than the maximum possible tilt. And above that critical value, the velocity increases at low inner radius but decreases when the inner radius becomes too large. And this implies the presence of two competing effects affecting the terminal velocity. To explain this trend, we consider the no-slip condition once again. And first, we see that due to the rotation in the plane of the ring, the contact point has the velocity as such, whose vertical component will balance out the downward velocity of the ring to maintain no slip. And the effect of drag is also more significant due to the large surface area, resulting in a lower terminal velocity. For a ring with a larger inner radius, the upwards component of the velocity due to the rotation in the plane of the ring will be much greater. To satisfy the no-slip condition, the center of mass velocity has to be greater as well. And at the same time, drag force will be smaller, as the surface area is smaller. But at a higher inner radius, we still see a decrease in the terminal velocity. This is because the effect of drag will be in fact more significant on a ring that's much smaller, as the ring is much lighter at a larger inner radius, thus decreasing its terminal velocity. When we vary the outer radius of the ring, the terminal velocity decreases. Similar to when we vary the inner radius, we know that beyond a certain critical value, the ring cannot achieve terminal velocity. To qualitatively explain this decreasing trend, let's consider the geometry of the ring once again. A ring with a smaller outer radius is a smaller tilt. Hence, the center of mass of the ring is offset less, and the contact point will have a velocity component, and the contact point velocity will have a greater vertical component. And as the outer radius increases, the tilt increases due to the greater torque required to maintain a steady precession. The center of mass is offset more, and the contact point velocity has a much smaller vertical component. Now, allow me to discuss the transient motion of the ring. To model single contact, we just need to make some slight modification to the double contact model.
Since the position of the ring is no longer constrained by geometry, we replace the height of the center of mass with two additional transmission degrees of freedom, the height of the contact point and the polar angle of the contact point along the rod, as shown in the diagram here. Considering both sticking and slipping at the contact point, we write out two different sets of equations. For sticking, we write out the force, torque, as well as the vertical and tangential no-slip conditions to numerically solve for the 5 unknowns. For slipping, we replace the contact forces with expressions for kinetic friction and normal force. And with the same force and torque equation, we can numerically solve for the 6 unknowns. And here's the computational flow of our numerical solver. The code solves the process of equations interchangeably, depending on the slip and non-slip conditions as shown here. Plotting the theoretical transient motion, we know that the contact point oscillates up and down continuously. And comparing it with our experiment, we see that there's a good agreement. And this oscillatory motion is a result of the rapid transition between sticking and slipping of the contact point, which was also predicted by our theory. And this causes steady motion arising from single contact. We'll quickly transit to double contact, to the top by weight about the contact point. In conclusion, I qualitatively explained the transition of single contact to double contact by considering the torque acting on the ring. I've also experimentally verified and explained the non-slip condition and qualitatively explained the factors affecting terminal velocity. The ring's motion was also fully modeled by considering the force and torque acting on the ring to obtain both the steady state and transient motion of the ring. And energy dissipation through rolling friction and air drag was also modeled quantitatively. Lastly, I've experimentally verified the geometric conditions required for steady state and studied the effect of inner, outer, and rod radius on the terminal velocity. Here are my references, and thank you for your time.
The opponent to the reporter, so please, 2 minutes.
Right, so my first question will be regarding the drag coefficients. Because you mentioned there are air drag. How did you determine the turbulent drag coefficient?
Let me go to my drag coefficient slide. So we characterize it using a pendulum. So you attach the...
okay, so am I getting correctly, the angle of attack of the relative motion of air and the ring is 90 degrees in this case?
We swing the ring like this.
Okay, right, thank you. And for the slide about your limitations, am I correct in saying that the tilt angle is the only limitation in your experiment?
Could I clarify what do you mean by limitation?
For example, you can vary the inner ring radius or to like increase or decrease the theta. Is there any other mechanism that could limit your experiment, limit your theory?
I believe that coefficient of friction will also be a relevant factor of assessing this.
Okay, since we're on the topic of friction, am I correct in saying that you did not assume sliding friction?
Yes, I assumed rolling friction.
You assumed only rolling friction? You assumed only rolling friction?
Yes, the contact point is not moving.
Okay, in which direction does the rolling friction point?
And I also assumed static friction. So it's a combination of both.
Okay, right. And can you go to slide 35, please?
35?
What would be the model behind this space plot?
Sorry?
What would be the model behind the green and red region?
The what?
The model. So what's the model behind?
Oh, the model is from here. So basically, we know that when
okay, next. Sorry. I have to interrupt you here. Can I go to slide 26, please? Yes. Why is
time? Sorry for that. You still have time in discussion. 3 minutes for preparation for the opponent.
So now we will start to
Your time for preparation is over. Please start your speech now. Your time is running.
Okay, so while they're preparing for the presentation, okay, right, welcome to my opposition on problem number 3. I'll ring around. First of all, let's take a look at the task statement. And our interpretation of the task would be to investigate the quantitative and a quantitative explanation of the motion in different states, as well as the parameter dependency of terminal velocity. And we thought the task is partially fulfilled. Moving on to the outline of the report. First of all, the phenomenon was well demonstrated in my opinion. In our opinion, the phenomenon was well demonstrated with the help of high-speed videos, which we find really well. Now, for the quantitative explanation, it was decent. However, for the energy dissipation, I think the reporter did not address the issue of air friction, air resistance very clearly, since his drag coefficient was not clear and the angle of attack was rather wrong. The experimental verification with that is very good because they had different plots showing the different phase plots as well as model predictions showing the comparison between the experimental results and their model. However, by the transient regime, I have another problem with the report, which is that they have actually made some false assumptions, which I will elaborate later on. Now, moving on to the strength and weakness of the theory. First of all, there were overall elaborate theoretical framework, which is very well done. And the assessment of the relevant forces, except friction, which is one of my main problems with the report, was very clear. Then the coordinate system and as well as the Euler angles were very well chosen, and the noted constraints were verified. Now, however, they cannot quantitatively explain the case where the steady state, they cannot really explain uppercase at the steady state. They tried to do that with the transient phase, however, I don't think that was done enough. And used turbulent drag without actually experimental verification. They used a simulation, which doesn't really show, under normal case, it doesn't really show what was happening. And also the drag coefficient has a rather, I think that's a huge deviation right there. And also they assumed constant contact during the transient phase, which I assume not to be true because the ring can actually oscillate between the two ends. Like there could be phases where there are no contact points. This topic I will carry on the discussion. Now, moving on to the strength and weakness of the experiments, there were good agreement for the phase plot, which I like very much. And you can both qualitatively and quantitatively explain what changes with each parameter, which is very nice. And there were overall good agreement with theory. Now, there were some missed parameters that were not investigated, such as the coefficient of rolling friction, as well as the drag coefficient. And also, on slide 9, as well as slide 24, I believe, there were severe shaking of the rod that we have observed. And this is also one of the relevant topics I think the reporter should have addressed in his presentation. And the inner, and also the quasi-steady state, which is the transient state, it didn't really show a good agreement in our case. However, they don't really, And the air drag measurements is inappropriate because they assume the 90-degree contact angle, which we believe not to be correct. And there were no investigation regarding the parameter change of threaded rods. That was completely missing in the report. Now, I would like to move on to the discussion.
Please, 10 minutes for discussion.
So maybe as a question at the beginning, could you maybe show me the slide where you verified the no-state condition?
All right. Hello. So I believe that you are referring to the slide. this slide, is it?
Yes, maybe what is, like, your concept explain what is really happening?
Like, essentially, the contact point is stationary with respect to the rod. So hence, that's why you can the contact point isn't slipping. And in fact, we also
sorry to interrupt you, but like, why is only in the green region is the X constant?
Because in the green region is the point. So essentially how we do it is we draw a marking on the ring, and then we spin the ring on the rod. So when the marking is in contact with the rod, its instantaneous velocity will be 0. And that is the green region that we are looking at. So you can see that in the green region, the gradient is actually 0. So that would imply that the velocity in the green region is 0, and hence the contact point is sticking.
What is actually the physical meaning of other points outside the green region?
It's just the velocity of the marking on the ring when it's not in contact with the rod. So it's just the velocity track.
Okay, so are you saying you have around 5 contact points to verify the no slip, like 5 data points to verify the no slip condition?
Yes. Yeah, so remember that in our equation we have this equation is that. So if we simplify this equation, we will get the equation in the yellow box below. So if we, and then we track the psi dot and the phi dot. So the psi dot is a spin angular velocity and the phi dot is a precession angular velocity. So we relate those two, and and the first condition is indeed experimentally verified. So you can see
Okay, right. I agree with the reporter on this case. However, I see that it has been experimentally verified. However, I think this graph would have been more appropriate to that you are presented during this lecture. However, I would like to move on to the transient state. So you have modeled this quasi-static motion, right, of the ring during the transient state using the Ronda-Kutta method with the differential equation.
Yeah.
Okay. Right. I assume you have always assumed like there is constant contact of the ring and the rod. Is that correct?
Yes. Yes.
Have you experimentally verified that?
Yeah, of course. In the ring of the rod, the ring is always touching the rod. It's not. I believe that it's not very interesting to just investigate something like this and just falling down like this, right? And then the rod you just up. It's not interesting to investigate. So yeah. So
okay, right. I agree. In this case, there is no friction, no normal force. Yes, yeah. But however, I think this is part of your this is part of the transient phase. Do you agree with that?
Yeah, of course.
Okay, but your model does not account for this phase.
I mean, it can account for this by, so we actually, isn't this case quite trivial since it's just half GP squared, like?
Yes, but like, did your, because you had a continuous plot, but if you ever encountered this situation, do you just have a gap in your model with your differential equations?
Yes, I believe that Ronda-Kutta method can actually detect this. So when the normal force becomes negative, it means that the ring loses contact with the rod. So that's how we know that the ring actually is not touching the rod anymore.
So you're saying this is in your quantitative model?
Yes,
Is that correct?
It's when the normal force is negative, so the system becomes unphysical, and hence we know that the ring is not touching the rod anymore.
Okay, yes. I agree that if no force is smaller than 0, it loses contact on the rod. However, I don't think this model would actually be, I don't think this model actually includes this because this model is based on the forces that act on the contact point, which I think would completely stop to make sense in this case. Right, I would like to move on as well. So let's move on to the steady state, where we have the force balance and torque balancing. You have mentioned about energy, about dissipated forces. Now, you have mentioned about rolling friction. Is that correct?
Yes.
Okay. How did you determine the coefficient of rolling friction?
Yeah. So how we determine it was we use we use double-sided tape and we take a few rings together.
Okay.
And after we roll down a piece of tape, which is of the same material as the rod. Yeah. And then from there we track the position times graph and we fit the theoretical curve to characterize to
obtain the rolling friction coefficient?
Okay, right. So you actually use the outer surface, the outer ring, the outer circle of the ring for the coefficient rolling friction. Is that correct?
Yes.
I would disagree with you in the sense that I think rolling friction would be very sensitive to like material in terms of wear and tear. So I think in this case it would be more appropriate if you use the inner ring instead.
Yeah. So essentially, how we obtain our ring is that it's printed, it's laser cut using acrylic. So the rationale behind this was because when we spin a metal ring on a rod, its inertia will try to vibrate the rod, hence energy will be dissipated through the vibration. And we don't want that to happen. So instead, it's a much better ring here. And since it's laser cut, it's laser cut. So the material, the surface property of the inner and the outer part of the ring will be exactly identical.
Yes.
So hence I believe that it will not be very significant.
But in my opinion, because rolling friction, there are no clear literature value of rolling friction on the internet, and that is because rolling friction is not always constant in the sense that, like, even the same material could have different rolling friction constants, because like small crevices, for example, inside the material could actually increase or decrease rolling friction constant drastically.
Yeah, but I think that since we have experimentally characterized the rolling friction coefficient, that is not really a major concept in our team.
I believe we have reached a disagreement here because the reporter seems to think that the inside and outside of the ring are of the same material, that's having the same rolling friction constant. However, I think it really depends on because rolling friction is really just a deformation of the material, so I think it will be more appropriate if you really use the contact surface. However, let's move on. So you mentioned about air drag. So you said you determined the air drag, coefficient of air drag by swinging the pendulum, swinging the ring on a pendulum. Is that correct?
Yes.
Right. Yes. However, in this case, I believe the relative motion of the air and the ring is directly perpendicular. However, is that the case when the ring is in steady state?
Yeah. So actually in experiment we also observe that happening. So that essentially instantaneously the airflow is always perpendicular to the direction of the ring's motion. It's always parallel to the direction of the ring's motion. So actually, what you will see is that in the pendulum case, the ring is going back and forth like this.
Exactly. Yes.
But when we put it on the rod, the ring is essentially tracing out the center of tracing out the vertical part.
Yes.
So it's essentially sweeping out the helix.
Yes.
Yeah. So the direction of airflow is still parallel to the direction of the ring's velocity.
Sorry. Again, I have to. Again, I'm sorry. Again, I have to disagree with you here. I think. Can you pass me the? No. Thank you. Right. In my opinion, I think the ring actually, the relative motion of air would actually be horizontal in this case. And with that, we actually don't have a 90-degree attack angle, but rather the theta, which is a tilt angle, that impacts the ring.
No, I'm thinking that if the ring is tilted like this, the airflow will be like this. And the ring is tilted like this, the airflow will be like this.
So you're saying it's always perpendicular?
Yeah. So the velocity that I'm thinking is the velocity here and the velocity here.
Sorry, again, I have to disagree because the ring is moving rather in this direction, and the tangential movement I think is more important. Thus, the airflow should be horizontal in my case.
Okay, guys, did we conclude somehow? Is that?
Okay, right. So thank you. Thank you for the reporter for this productive discussion. So a couple of the points that we touched upon. Maybe I will restate two of the main disagreements we have. First of all, against the end, we have the air drag pendulum measurement, and in my opinion, I believe that this measurement is rather inappropriate because it assumes the wrong air attack angle of the airstream and the ring relative motion, which the reporter seemed to assume with 90 degrees. However, I assume it should be horizontal, it should be equal to the tilt angle. And for the coefficient of rolling friction, because the reporter used the outer ring, the outer circle of the ring as a measurement point. I do not consider that to be appropriate because coefficient rolling friction is highly sensitive of like little cracks. So I think the reporter should have used the real surface of contact. And yes, thank you.
Are the vibrations source of this pressure?
Yes, but not in our
Yes.
experiment.
What do you think about this?
So can you restate the question? What
Are the vibrations cause of energy dissipation?
The vibrations of the rod?
Yes.
I don't think so. No.
Please go to the slide number 25 then, and in the meanwhile, yeah, and please play this video. Yeah, question to both of you. To the opponent. Is it significant? The movement of the rod in there.
Like what I said previously, we switched from using metal washers to plastic washers to prevent the vibration of the rod.
Okay.
So I believe that this
With what part the ring touches the rod?
The
edge or flat surface?
but the ring,
edge or
with
this flat surface?
In the ideal case, it's the edge, but in this case,
Okay. So do you think that rolling friction measurements were conducted well?
Actually, well, first of all, that is a good argument. I don't think so. Because,
yes or no, please? No. Okay, thank you. Do you have a plot on how inner radius of this changes the rolling friction?
the inner radius changes the rate of friction.
Yeah,
No, I don't.
Okay, thank you. Please go to the slide number 61. Do you have a photo of experimental setup for this?
No, we don't.
No? Okay. And do you think, the opponent, that flow with this situation is the same with the situation where the rod is inside?
no, I don't think so.
The same question to you?
I think that's a good enough. It's a good enough approximation.
Thank you. Are the initial conditions important in this problem? Firstly.
To calculate the terminal velocity, they are not important.
Okay. And do you think initial conditions are important?
I agree with the reporter that steady state it is not, or in transient state it is.
Did you control the initial conditions in your experiments?
For transient state, yes, we did. For steady state, no.
Okay. So please go to the slide number 35. And what are initial conditions in this situation?
Because we are investigating steady state in this case, so we drop the ring by hand and spin it by hand.
Thank you. The next slide, please.
Okay.
And why do you think the theory on terminal velocity agrees there or not? First question to the opponent.
I think more it lies in the
error.
error. It lies in the error.
Yeah, I think personally, I think he agrees.
Okay. Why didn't you not? What are the discrepancies in velocity then? Because this is x over t. What is the discrepancy between your theory and experiments in terms of velocity?
The error bars are due to tracking error.
I mean,
Okay. That was the answer. So, Nicholas, thumbs up, and you have 2 minutes.
talk about the strong sides of the reporter, he analyzed two phases of motion in this problem. Also, he performed analysis for different number of points of contact, meaning 1 and 2, and we believe that this part was conducted really well, as well as all the 3D mechanics approach, of most of the 3D mechanics approach. We believe that was the biggest advantage of this presentation. They analyzed 3D geometry very well, as well as the force. They included anticipation of L in the form of air drag at rolling friction. We don't believe this is well done, but still we see that they considered it. Also, they predicted somehow terminal velocity and investigated parameters influence terminal velocity, inner radius and outer radius. In terms of disadvantages of this report, there was unclear air drag field. We all know that flow with the rod inside is completely different than the flow on a seesaw. Also, we didn't get to see the experimental setup for this measurement. That's why we can't verify whether this was conducted well or not. Also, they used only one rod and assumed that the friction is opposite to angular velocity. I mean rolling friction. We disagree with this, and we believe that rolling friction is such that it opposes the movement of instantaneous movement of point of contact. Also, they did position time graph instead of velocity graphs, and to talk about other flaws of this presentation. We need to get back to the problem statement. The problem statement clearly divides the phenomenon on 3 parts. The first part is sliding down. The second part is that it may start spinning, and the third part is terminal velocity. In our opinion, after this presentation, we still don't know when the rod may start spinning. And we didn't get any predictions and analysis on this. If you talk about the opponent, he investigated and asked about drag measurements, which we value a lot. Also, he noticed shaking of the rod, but didn't get in depth in this problem. Also, he asked about the type of friction and direction of rolling friction, which in our opinion was the biggest flaw of theoretical model. If we talk about the flaws of the opponent, he stated that not using threaded rods is a mistake. We don't agree. Also, there was no discussion of some relevant parameters. In our opinion, rolling friction discussion wasn't conducted well as we found with the initial conditions after this whole presentation, and notice flat versus edge differences in rolling friction measurements. If you talk about the discussion, the topics that were mentioned are the following. There was no sleep condition experiments, and we agree that the primary experiment of the reporter was unclear, and opponent well presented his statement. Also, they talked something about losing point of contact, and we agree that their theory predicts this, and it is actually the way to go. They talked about measurement of rolling friction, in which we completely agree with the opponent that it wasn't conducted well, as well as measurement of the air drag, where we also stand with the opponent. If you talk about the next parts of this presentation, the discussion, they didn't include tilting, like vibrations of the rod, as well as they didn't actually tell us when the terminal velocity is not reached.
Okay. Thank you very much. Concluding remarks for the recording, please.
Thank you to the author and the reviewer for the insightful discussion. So firstly, here are some of the concerns raised during the discussion. So firstly, I would like to clarify that energy is dissipated through rolling friction and air drag, which was modeled in the theory. And for rolling friction, the rates are very thin. So the concept of edge only exists in the ideal case, and in reality, it's more of like a rounded edge due to the imperfection both around the surface, which is also the reason why rolling friction arises. And rolling friction dissipates energy, and it's not dependent on the contact point velocity, as mentioned by the reviewer, since the contact point must be sticking fast to use rolling friction. And for turbulent drag, the radius number is actually very large, so it's around 4,000 as calculated. So the airflow is actually turbulent, and hence the drag is proportional to V squared. And the power dissipated is proportional to V cubed. Yeah, so, and for the angle of airflow, the ray is moving and thus creating a gravity airflow. So airflow is always perpendicular to the surface of the ring. And the velocity used in power dissipated by drag is also the component of the velocity normal to the ring. And regarding rock shaking, so we use light laser cut washer, which is going to shake the rock significantly. And the shaking of rock for plastic washers was also not observed experimentally pretty significantly. And for pelleted rock, we did attempt to try using a pelleted rock, but we chose to focus on a smooth rock instead of investigation because we believe that it's actually more interesting. And for zero contact with rock during transient motion, we believe that no falling of ray contributes no further physical insight into the phenomenon, and hence we do not really investigate this in depth. Yeah, so in conclusion, I qualitatively explained the transition of single contact to double contact by considering the torque acting on the ring. I've also explained the advanced information and qualitatively explained the factors affecting terminal velocity. And the ring's motion was also fully modeled by considering the force and torque acting on the ring to obtain both the steady state and transient motion of the ring. And energy dissipation was also modeled quantitatively through rolling friction and air drag. And lastly, I've also experimentally verified the conditions required for steady state and vary the effect of inner, outer, and rock radius on the terminal velocity. So thank you.
Okay, thank you very much. As usual, can I ask all the reporter, opponent, and reviewer gathered here at the stage? You get 1 mic to share. And time for questions. Mikhail and then Natalia.
All right, thank you. And to the reporter, so for example, you also had on some slides, you had like a reference to a paper, for example, on slide page 29. Can you also quickly clarify which parts of the theory will I find in the papers and which one is from you building up on the papers?
Oh, actually, most of the theories are original except for the part where we model energy dissipation through rolling friction. Yeah, so this part was the part where we referred to a paper to model the energy.
All right, thank you very much.
Okay, thank you, Natalia.
Slide 36, please. Yeah, so here it seems like for the yellow and the orange, the theory underestimates the experiment, right? Like it's a systematic deviation, so where does it come from?
It could be due to either the drag coefficient or the rolling friction coefficient not being very accurate. Yeah, because I do agree that swinging the ring around a pendulum is a slight signification, but yeah, so the drag in reality could be slightly higher than that. Yeah, so that's the reason for the deviation.
Okay, so in the theory there are no fitted parameters, like they are just independently measured.
Yes.
Yes. Okay. Yeah.
Could you go to slide number 4, please? Just quickly, what is more or less the theoretical equation on your theoretical line?
Sorry, could you repeat?
What is the theory? How does it look like, the equation? And also the type 1, what it's supposed to look like?
So the theory is basically this energy balance. Yeah. So this energy balance. There's no analytic equation for this. Yeah, so it's all numerical.
Okay, slide number 48. Oh, sorry, not the. Okay, the thing is like, would you call this a theory experiment match?
I would say that for the first half of the graph is a decent match. So you can see that the period is roughly the same. So that actually, yeah, and the reason why it also sounds like now is because of the mutation of the ring. But for the behind part, it doesn't really fit because the motion of the ring is rather chaotic and it's a bit difficult to get the right initial conditions to input the numerical simulation. Yeah.
Okay, thank you. Peter and Natalia again. Peter first.
Yeah, no.
Okay, that was a quick, I love this kind of question. Natalia.
Can you show me slide 25, please? 25.
25.
Right, with the green region, please. So, how did you aim, like, do you think this is a straight line? And B, how did you decide it's straight exactly there?
Okay, it's probably like, or maybe straight and horizontal, isn't it?
Yeah, sorry, horizontal. Thank you.
So, I mean, you just look at it and it looks quite flat.
Yeah, what about like moving it 2 points, 3 points to the left? would be putting stress on?
Oh, because from our video footage, it's very difficult to determine when exactly is the contact point, when exactly is the marking on the ring touching the rod. So it's a region of contact.
Okay, do the opponent and the reviewer agree to this?
I would say, I mean, he showed me during the discussion another slide where he verified essentially also the non-slip condition.
Yeah.
And I think that one was rather sketchy, but the other one was good.
Second review.
In my opinion, it's extremely difficult to measure that, and this is probably the way to handle this.
Okay, Gavin?
Does your theory actually take account of the ring thickness itself?
Oh, no, it doesn't. Because the ring thickness will introduce a lot of complexity in the theory. So in our experiment, we actually try to...
Thank you. So if it was, what would be the effect of a thicker ring of a given mass?
The most straightforward effect would be the moment of inertia. And maybe the true angle will also maybe change a bit because of the thickness of the ring.
Okay, Xiaoyang, and me.
Quick question for the reporter. Quickly, how do you determine your tracking error?
The tracking error. Basically, we track the video for a few different times, and then we take the standard deviation of that human tracking error.
Yeah, please slide me one. 21.
2-1.
Meaning of this slide in one sentence.
No, this is like, okay, if you can manage it in one sentence, but like, please not a sentence.
Yeah, okay.
But it's just expressing the angular velocity as three different components along the principal axis of the ring.
Okay, I have one quick question because you discussed on the vibrations, and basically your defense was that then later we use this like lighter weight. So why don't we have footages of like movement covering these lighter washers? So why your videos show the vibrations if you claim that in experiments they were not present? In your video recordings, we see massive vibration of the rod. If I understood, you said this was not a problem for the experiment because you used light washers instead. So why haven't you exchanged your video recordings with this new experimental setup?
Because the phenomenon is clearer with like for the plastic washers, it's a bit hard to.
Okay, I see. And then various question, Natalia.
So did you change the friction coefficient of the rod?
The friction coefficient.
Yeah, did you friction coefficient in your measurements?
Oh, the friction coefficient. The kinetic friction coefficient does not affect the motion. It's the rolling friction coefficient. And for rolling friction, we use the plastic ring.
So would there be any qualitative change to your result if you vary the?
Yeah, yes. Never.
But you haven't investigated that.
I've investigated the effect of sliding friction.
Okay. We see the slide that you can give it there. That was it. Thank you very much, everyone. That was it. Final role of setting up the grade for the first stage and basically setting the.
I'll let you have it. I'm not sure if I'm not going to say it.
I'll also do my job.
We'll meet again. We're going to go to a flight together.
Oh, flight? So like in the middle of the 5
Yeah, and we're playing this game together later.
See you. Yeah, very nice to meet you.
Okay, give us a few more minutes. I can see that the jurors are, coming back into their notes and clearing, what they gave earlier today. So it's harder and harder job for them. So, what are the classes of different things?
Being out of the university, my way.
Singapore as usual, or Poland as the last year's Poland as the last year's winner, or Switzerland as the black horse of the competition.
Actually, I'm not sure. Isn't there?
There might be, but then
I would be lying if I would say I have no better idea.
I'm not sure.
Watching the grades.
I'm very nervous.
But we are very close to having the final day. I want to see you sum it up for. Oh, you have to round. This will be the decision. Yeah. There was a case in the final when a single grade of a single juror for a review finally made the difference for the point mark. So it really goes down on each single jurors, which doesn't make the pressure of your final. Okay, we're done. Gavin is finalizing.
Bármit most még Magyarországon nyerni, aminek fehér.
Okay. Yes, we have everything we need. You might need to sleep for now. Okay. Grade for the report. Now, 7, 8, 9, 7, 6, 7, 9, 8, 7. 7, 6, 9, 8, 7, 8, 9, 8, 8. And finally, grades for the review. No. 7, 6, 8, 8, 7, 8, 6, 6, 6. You don't need to calculate the grades. They'll be good very quickly and immediately after the questions or the explanation of the grades from the jurors. I'll tell you the results, but give now the chance to the jurors to explain their grades. We have a good spread again for the report. There was a single 6 by Gavin.
Okay, I was quite happy with the report in many features. Certainly the analysis was great, but to be honest, I was a little bit underwhelmed by the comparison with the theory, bearing in mind that you didn't seem to have varied that many parameters with regards to the different rods, they're easy obviously to have changed. I do like the fact that you measured quite indirectly the coefficient of drag and draw. I was grading it relative to the others, and it's slightly weaker than I've seen earlier on. My partial grades were 1, 4, 1.5, and I subtracted 1, 2.
Okay, thank you very much. And we have 2 9, so maybe, I don't know, Kerry, would you take the report and Nina then take the opposition?
Yeah, well, I'm sorry, yesterday to get the high grade, and I'm still pretty good to get the high grade. I think the opponent figured out some weaknesses, and then of course the final show up, but slightly higher than the top grade, I think it's 6,
Okay, so it's really high, really nice score for the presentation itself. Thank you very much. For the opposition, so Mikhail, that you.
Alright, so I have the lowest grade of 6. The partial grades are 4, 1.25 for the questions, 2.25 for your position speech, and 2 for the discussion. And it comes up to like 6.5, and I decided to round down, mostly because I need to be consistent with the other grades, and I don't think that this opposition was much better than the one before from Singapore, which I also gave a 6. And I think that is true because in your opposition speech, this was already pretty nice. So this one was still quite nice. So you noticed, for example, that the motion is definitely like the weak point of the report. But other than that, you really try to criticize, like you really try to be critical, but it always fell a little bit flat. And I also think that in your discussion, you should have been able to discuss more things. You also needed to really think about what is actually happening right now and what needs to be happen again. And for example, some things which I found were somewhat obvious in the report, you were a little bit of struggling with. Of course, sometimes it was also clarified. And then the suggestions that you did give, for example, just an example, I'm not saying this was the reason, but just as an example, so that you should have, for example, that the reporter should have, for example, used the surface that actually touches the ring on the inside to use the friction measurement. I think with the reporter's method of like cutting it out, it doesn't make a difference, but you could have at least suggested a method of doing it if you want, if you think this is relevant, you could have just like put the rod horizontal.
Okay, okay. Thank you, Matt. And Nina, 49.
Yes, I really like the questions. It would have been more or less my questions as well. Most of them leave with Michael, pretty much the same ideas, but I've seen it in a different way, because you have spent relatively a lot of time on given topics or questions, and because they were easy. I mean, you have a lot of questions, very, very friendly, or a little bit less questions, but you had the chance to discuss about it somewhat deeper, and more obviously even the actors needed some time, so that reduces the number of it. But
I ended up with 1, then the beginning 1.5 with the questions, 3 and for the speech, and it was 8.5, and I run it up, so I forgot the time. Forgot totally about the time. I just each your discussion, and that was basically the reason even for the 9 of the reporter, even though that was obviously not a perfect solution, that was an 8.5 also, but because the discussion was so amusing that I had to run it up.
Okay, yeah, I've seen him. I told you, like, thinking a lot about where to round up or round down, and then finally we have the rules, so there are 4 6s on the lower side. Dalia, would you like us today?
And so I gave you 1.5 for the questions, 0.75 for the review of the position.
Maybe can you change the microphone? I think that one is running out of the battery.
And 0.75 for discussion analysis and 0.25 for the basic points, plus 0.5. Yeah, so for these points, for example, I'd like that you mentioned the source of dissipation, which was also something that I then asked in the jury questions. Right, yeah, I also like that you pointed out the systematic shift, well, like in a similar point, but also in the questions. I also like that you pointed out that there was no discussion of parameters altered in the review of the opposition. But overall, what I have to say I liked in your review was prioritization. Like we saw so many points in the slides, and then maybe there was 1 or 2 bolded, like highlighted, but I would appreciate maybe there being a little bit less point that being really clear what you consider important. So I think that's why I subtracted mostly in all of the sections.
Okay, yeah, I just one thing is bolding it, and the second thing is maybe again choosing the more important parts and maybe investing a bit more comments from them, because you basically spend a lot of time reading all the comments, and even okay, if they are all stated there, maybe for the speech itself, it's better to concentrate, just we can read most of the yours open. So just concentrate on a few of the really important topics and discuss them more into detail, because I was really lost in the huge amount of topics, some of them more relevant than the others, so that's why I was like very close between 6 and 7 and then I ended up with 6.
Just one small thing, I liked your own opinions in the discussion analysis. There was just summary, there were no your own opinions, so I couldn't give it like that.
Okay, anyway, KPM 8.
Thank you. So I really like your question asked. So that's fast, and I see that you understand the report and the discussion. So I give a 1.5 to the question asked. And after that, there was a really good overview of the report and the opposition. So I give you 2 to the review of the report and 2 to the review of the opposition. After that, I agree that you should show your own opinion better in the discussion analysis.
Okay, I just we can continue the discussion, but please, guys, this was discussed. Put the grades now into the system. We'll check it afterwards. Put the grades now into the system. This is how it was discussed. Now, like, I know you have been doing it differently before, but now just put the grades into the system so that we can just get the result. They might be wrong, we'll correct it. No, but like, the probability is rather long because I've checked the score sheet. I kind of remember 8 or 9 numbers, so there shouldn't be a big issue. But we don't want to wait, scan the score sheet, and then like script the work. So back to Peter, I just wanted them to start typing again. So Peter, it's your turn.
I forgot to confirm what I, but I gave 1 point to the discussion analysis, and I think you gave some other missing points in this part, so I gave also 0.5, which is missing points point out, and 0.
Okay. Yeah, thank you very much. So let's give once again a big applause to all 3 teams.
And now I think we are very close to getting the results because I see Jan already writing something on a sheet of paper. So he knows, I don't know yet. I just wanted to mention one thing which I realized while looking at the selection of the problems, and this is also maybe a bit of a message to Samuel and all the other committees, like, you know, we're discussing that we're always saying, oh no, we want it more complicated, more elaborate process, etc. But in the end, for the finals, like we had one, say, purely mechanical problem, then we had a problem which was certainly not easy, but it was kind of like conceptually not a very complicated problem with the potential line. So in the end, I believe like the students tend to choose something which is say conceptually a bit more easier. So maybe like we have to think about that as well while we selecting problems.
Oh, even an envelope. Open too many numbers because that's the back side of the sheet. Woo!
Third place, 38.5 points. The team from Poland. We go above 40. Second place, 42.8 points. The team from Singapore. From Switzerland. Because I think we have really seen a very nice finals with very nice presentations, discussions, and everything. Thank you, jury members, for serving in. I wasn't very wrongly that much happy after yesterday's winery, and some of the jurors were even less happy. But then everyone finally agreed to be here. Thank you for that. And yeah, we'll have a closing ceremony with all the awards, etc. in the afternoon. So please now. Behind the shield, as usual, we have an hour stayed from the opening ceremony and we'll probably continue till the closing ceremony, but we'll do our best to start at 3 o'clock with Aula Magna, so one for us. So,